I announce future classes in WhatsApp groups. You guys can join those WhatsApp groups. Just message me here. I'll send you the link. This is my number. You can message me here and I'll send you the link, right? So we'll be continuing from where we left off in the last class. In the first part, but since I am consolidating it, मेरा lecture उधर से ही continue होगा. My lecture will be continued from the very moment that I left off. But obviously for you guys, it's part 2. For the students who are registered on the portal, it'll be a single part. It's probably going to be a 5-hour marathon in totality. For you guys, about 3 hours are done, 2-3 more hours are left, right? So yeah, I'm going to start the recording now. Hey everybody, so let's continue. Yesterday when we talked about all of these things, we were basically talking about our mind map, and we were here, right here. We were done with alkenes, we were done with alkenes, and we were also done with haloalkanes to some extent. How are haloalkanes made? So they can be made from alkanes, they can be made from alkenes, they can be made from alcohols. And for alcohols, it depends. If you want to add a chlorine atom, you have to have those conditions, and if you want to add a bromine atom, the conditions are different. If you want to add an iodine atom, the conditions are different, right? But now we're going to study, okay, we now know haloalkanes are made through alkenes, they're made through alkenes, they're made through alcohols, but they also have certain reactions, right? And the first reaction, we had already studied that, the reaction number 9, which is haloalkanes to alkenes, that is sodium hydroxide ethanolic and heat under reflux. And this is obviously an elimination reaction, right? We wanted to talk more about haloalkanes into amines and haloalkanes into nitriles and haloalkanes into alcohols. Let's first discuss them. So yesterday we left the class right here. So haloalkanes into alcohols. Remember, all of these three reactions, haloalkanes to amines, haloalkanes to alcohols, haloalkanes to nitriles, all these three reactions, they are basically nucleophilic substitution reaction. Now, why are they called nucleophilic reactions? Nucleophilic because the reaction is initiated by a nucleophile, right? Just like when we were talking about alkenes, we said, hey, in alkenes reactions, it's called an electrophilic addition reaction because it's initiated by electrophiles, right? That's what starts the reaction mechanism. But later on, when you study the alkene electrophilic addition reaction, you also realize that when a carbocation intermediate forms, it is attacked by what? It's attacked by a nucleophile which formed due to the heterolytic fission of the Cl-Cl bond or the HCl bond, right? So you realize that there are nucleophiles and electrophiles involved in mechanisms to some extent, but you also then understand that, hey, even if there's a nucleophile involved, even if there's electrophile involved, it's the starting phase is what determines the name of the mechanism. So since the reaction was initiated by an electrophile in alkene reaction mechanisms, we called it electrophilic reactions. These reactions are called nucleophilic reactions because it's initiated by a nucleophile, and I'll show you the mechanism in a while, since that mechanism is in fact part of your course, right? And it's called a substitution reaction because an atom or a group of atoms are substituted by another atom and no single product is formed. There are multiple products which form, right? So it's not a single product forms, unlike in an addition reaction. So these are all nucleophilic substitution reactions. Let's first discuss haloalkanes into alcohols. Now, how do you take haloalkanes into alcohols? The conditions for this fella is sodium hydroxide, and remember, it's aqueous right now, and you heat under reflux. Why do we heat under reflux? The reason why we heat under reflux is because haloalkanes and alcohols, they are both very volatile, so we don't want these haloalkanes to escape, right? And because we don't want them to escape, since they are volatile, we heat under reflux, where we add a vertical condenser, and that basically condenses the vapors, which are the volatile vapors, and gives you a good conversion product, right? So that's the reason why we heat under reflux. The question is, why do you use sodium hydroxide aqueous? And remember, in organic chemistry, wherever you're using sodium compounds, you can also use potassium compounds. So you can also say potassium hydroxide aqueous, but there's a story to it, right? Potassium hydroxide aqueous or sodium hydroxide aqueous, why do you use it aqueous? Now, you have studied haloalkanes reaction mechanism, in which you learned how haloalkanes go into alkenes, right? Although this reaction mechanism is not part of your course, but in this case, you used sodium hydroxide ethanolic and you heat under reflux. Now that's a very, very thin difference between haloalkanes to alkenes and haloalkanes to alcohols. See, in both cases you're using sodium hydroxide, in both cases you are heating under reflux, but the only difference is if you take haloalkanes and sodium hydroxide is aqueous, you're going to end up with alcohols, and if you take haloalkanes and sodium hydroxide is dissolved in ethanol, you're going to end up with alkenes. Now obviously this reaction mechanism is called an elimination reaction, and the other fella was obviously nucleophilic. This fella right here, this is called nucleophilic substitution reaction. Now why does this happen? The why is not part of your course, since you don't need to know the mechanisms for elimination reactions, but I want to teach you guys the mechanism for it. I've also taught it in the first part, but I want to teach you the mechanism for you guys to understand the difference between sodium hydroxide being dissolved in ethanol and sodium hydroxide being dissolved in aqueous solution, because that is what will help you remember it throughout your lives. This is how I've remembered it. I've never learned any reagents. No, it's all conceptual. I tell you how it's conceptual. The idea which takes place is that when you take sodium hydroxide and it's dissolved in ethanol, hydroxide ion is very, very special, because this hydroxide ion can behave in two ways. This hydroxide ion can behave as a base, and this hydroxide ion can also behave as a nucleophile. Why can it behave as a base? You've studied this in O level and IGCSE, that hydroxide ions are effectively bases because they are proton acceptors. And why can it act as a nucleophile? Because the O basically has a lone pair, so it can act as a nucleophile and it can also act as a base. The question that you all need to ask is when will it behave as a base and when will it behave as a nucleophile? If sodium hydroxide, or if the hydroxide ion is basically in ethanolic condition, the hydroxide ion will behave as a base, and if it is aqueous conditions, the hydroxide ion will behave as a nucleophile. And let me show you how it works. So basically, if you have a haloalkane that looks something like this, I'll just take bromoethane for example. What you do is you take the sodium hydroxide and dissolve it in ethanol, and the moment you do that, you realize that hey, if you dissolve the hydroxide ion in ethanol, it will behave as a base, and behaving as a base means what? It's a proton acceptor. So the lone pair is going to attack this hydrogen right here. It would want to accept this proton, and we know that hydrogen can't make two bonds. So the moment the hydroxide ion accepts this hydrogen, the CH bond must break. And how does the CH bond break? So the CH bond break and both the electrons move towards the carbon-carbon double bond. And the moment this carbon-carbon double bond forms, the left carbon has now made 4 bonds. One bond here, and this will become 2 bonds. But the right carbon has made 5 bonds effectively. See, this carbon is gonna be making a double bond here, 1 bond, 1 bond, 1 bond. And we know 5 bonds can exist. There must be 4 bonds in totality for the rightmost carbon. So it must break one of the bond. And which bond ends up breaking? The CH bond or the CBr bond? Since the CBr bond is weaker than the CH bond, the CBr bond breaks and both the electrons go towards the Br atom. Why? Because there's electronegativity difference. This is also already a partial positive carbon, and this is already a partial negative Br, right? So both the electrons go towards the Br. Since Br is more electronegative, the electrons already lay closer towards the Br, and this bond breaks heterolytically, and effectively what happens is you end up with OH minus ion making a bond with the hydrogen ion and making H2O. You end up with the bromide ion. When the CBr bond breaks, you end up with the bromide ion, which bonds with the sodium ion and ends up with NaBr, and you end up with a beautiful alkene right here. And that's the beauty of organic chemistry. Everything is connected, right? And students and teachers alike who say this, that HBr is the fella which forms, that's absolutely incorrect, because again, the mechanism is not part of your course. But if you guys as Cambridge students think that HBr is the byproduct, that's absolutely incorrect. H2O is going to form and NaBr is going to form. There's no such thing as HBr forming. Yes, it's good to just use it as a rule of thumb that these two fellas are going to go away and there's going to be a double bond here, right? It's good to use it as a rule of thumb, but in reality, HBr does not form. Even Cambridge examiners, you can read the books for it, you can read the materials for it, not just use one book, use multiple books. If you're interested in chemistry, you can see the mechanism for this elimination reaction, and you realize that H2O and NaBr are the fellas which form, not HBr, right? Cambridge in their questions, they say HBr is formed. That's absolutely incorrect. Cambridge questions are incorrect because of this, and I wouldn't call them incorrect because they're also right in to some extent, because they know that you don't need to know the mechanism for it. That's why they simplify it by writing HBr, right? So that's the idea. This is how the elimination reaction takes place, because the hydroxide ion behaves as a base in ethanolic conditions. But if you take the same haloalkane, and the hydroxide ion is not dissolved in ethanol, rather the hydroxide ion is dissolved in, and I'll call this CH3. Instead of opening it up, I'll just call this CH3, right? So now, and I will, instead of putting the Br here, I just want to, format it a little for you all. I'm going to put a Br here, and I will put a hydrogen here and a hydrogen here. Now what actually happens is, if the hydroxide ion is not dissolved in ethanol and it is in aqueous conditions, this hydroxide ion will now behave as a nucleophile. It would not behave as a base, it would behave as a nucleophile. And what do we mean by behaving as a nucleophile? It would be attracted to nucleus. It will be attracted to positive centers. And what is a positive center right here? We know that the CBr bond, there's a separation of charge. Since Br is more electronegative than carbon, the Br is going to have a partial negative charge and the carbon has a partial positive charge on it, right? So you realize that the hydroxide ion, since it will not behave as a base, now it will behave as a nucleophile. It will be attracted to the carbon with the partial positive charge. So what will happen is the lone pair will attack this fella right here, this carbon right here, and the moment it attacks this carbon, the moment it attacks this partial positive carbon, we know carbon can't make 5 bonds, so it must break one of the bonds. And which bond does it end up breaking? It ends up breaking the CBr bond, and the CBr bond indeed breaks heterolytically. So this bond breaks heterolytically. What happens? You also show an intermediate in between. I'm not showing that intermediate right now because I couldn't care less for now. But what we realize, and we don't even want to call it an intermediate, it's just a stage which we want to show theoretically. It's just a theoretical stage which we want to show, but I don't want to show that theoretical stage as of now. That's why I've put a dash here, since I don't want to talk about the mechanism in its entirety. But when this fella goes there, the OH is going to be bonded right here to this carbon, and you end up with what? You end up with an alcohol, right? So you have C bonded to H, you have the OH right here, and you have the CH3 right here, and you had what? You had a hydrogen, another hydrogen, and you saw how beautifully the haloalkane, the CBr fella, was converted into the COH fella, right? And that's the beauty. In one case, you ended up with alkenes from haloalkanes, and in the other case, you ended up with what? You ended up with alcohols from haloalkanes. So that's the only minute difference between the reactions, and that's what we realize. If haloalkanes, we want to take haloalkanes and convert it into alcohols, what do? We use sodium hydroxide or potassium hydroxide in ethanolic conditions or in aqueous conditions. Obviously it must be in aqueous conditions because we want the hydroxide ion to behave as a nucleophile and we do not want it to behave as a base. That's the beauty. So that is how you go from haloalkanes into alcohols. And why is it called a nucleophilic substitution reaction? It's pretty easy. It makes sense. Why? Because see, a nucleophile, see right here, a nucleophile attacked this partial positive carbon. So the reaction was initiated by a nucleophile. And why is it substitution? Because a Br atom was substituted in place of an OH atom. Done? Okay. Now, that's the idea. Then, if you want to take haloalkanes and convert them into amines, you'll study more about this in A2 chemistry, but it's good to also know this right here. If you want to take haloalkanes and convert it into amines, amines are basically the NH2 functional group, the NH functional group, the N functional group, right? So if you want to take haloalkanes and convert it into amines, what you do is you use NH3. You can either use concentrated NH3 or you could use excess NH3, and you heat it in a sealed tube under high pressure. Now, obviously, there's reasoning to every single thing. And I'll try my best to explain every single condition to you, every single relation to you, just like I did with sodium hydroxide, aqueous, and ethanolic. I try my best to do that. But then again, I don't have that long, right? So I've explained everything in my live classes, every single reagent, every single detail. But since this is a marathon, I expect you guys to know to just take things as I say it as a factual statement. But obviously, I'll try my level best to cover as much detail as, even if it's not required by the exam, since I know that this, explain kacha, why would it be heat in a sealed tube under high pressure? Why do we use excess NH3? Why not just NH3? There are all these questions that can come in your brain, and you guys might think that, oh, chemistry is all rote learning because sir is making us trouble. No, I have not done this in my live classes. They all know why it's excess. They all know why it's heat in a sealed tube under high pressure. They all know all of that stuff. But since since obviously it's not part of your course, you just need to know it as I say it, right? But still, I'm going to discuss it in a moment. Okay. And then if you want to convert haloalkenes into nitriles, you use NaCN, sodium cyanide, or you could use potassium cyanide. Remember, in organic chemistry, wherever you are using sodium compounds, you can also use potassium compounds for it. So you use NaCN, and what do? You heat NaCN, and remember, NaCN should be dissolved in ethanol. And you heat, or you could say heat under reflux. Both are correct. Normally, I'd suggest writing heat under reflux since haloalkenes are volatile, right? So that's the idea. These are the three conditions that you need to know. These are the three reactions for haloalkenes, which is going from haloalkenes into alcohols, going from haloalkenes into amines, and going from haloalkenes into nitriles. And these are obviously the conditions for it. Now, obviously, you also need to know the mechanisms for it. And these reactions are called, all three reactions are nucleophilic substitution reaction, but there are two pathways that the examiner can take and that these reaction mechanisms can have. One is called the SN1 pathway, and the other one is called the SN2 pathway. And through this, you will also realize what amines are, what nitriles are, and what alcohols are, right? So one is the SN1 pathway and one is the SN2 pathway. Now, what is the difference between SN1 pathway and SN2 pathway? Basically, before I explain the difference between the two, you guys need to know what a tertiary haloalkane is, what a secondary haloalkane is, and what's a primary haloalkane. And the concept is pretty simple. Just like you learned about carbocations, a tertiary haloalkane is a haloalkane in which a carbon and halogen atom are bonded, but it's also bonded to three alkyl groups or three carbons, right? A secondary haloalkane is the fella which is bonded to two alkyl groups or two carbons. So I'll represent alkyl groups with R or carbon, and one is obviously going to be hydrogen. And the primary haloalkane is the fella which is bonded to one alkyl group or no alkyl group, right? So that's the primary haloalkane. Now, between these three, between tertiary haloalkane, secondary haloalkane, and primary haloalkane, which one is more stable? Between these three, which one is more stable? And the answer to that is, and this is where a lot of students get confused and they get things incorrect, they are all equally stable. They're all equally stable. Remember, it's not like carbocation intermediate, no. They're all equally stable. Yes, they will have different rates of reaction. For now, that's not my concern, but they are equally stable. Do not say that a tertiary haloalkane is more stable than a primary haloalkane, which is more stable than a secondary haloalkane. No, you just need to know the differences. Yeah, a tertiary is a fella which is bonded to three alkyls, secondary is a fella which is bonded to two alkyls, primary haloalkane is a fella which is bonded to one alkyl or no alkyl. A lot of teachers teach this incorrectly, right? So now basically what the reason why I told you guys this is in order to be able to understand the SN1 mechanism and the SN2 mechanism. And teachers butcher this concept, by the way. They butcher it, they make students rote learn it. There's no rote learning to it, right? Now, what exactly do we mean by SN1 and what do we mean by SN2, and when will haloalkenes undergo the SN1 pathway and when will it undergo the SN2 pathway? It's very simple. S means substitution, N means nucleophilic, and 1 means unimolecular. Now, what do we mean by unimolecular? Unimolecular means a single product, a single reactant is involved. A single reaction is involved in the rate determining step, which is normally the slow step. Sir, what in the hell do you mean by this gibberish? Let me teach you what I mean by this gibberish. Take it. If you have a primary haloalkane, which is carbon, let's suppose I'll call this CH3. I'll add one alkyl group here, I'll add a hydrogen here, and I will add a Br atom here, right? This is a primary haloalkane. We all agree that this is a primary haloalkane because see, a carbon which has the halogen atom is bonded to one alkyl group. We all agree this is a primary haloalkane. Now let's first talk about the OH minus, right? When would the OH minus act as a nucleophile? When it is aqueous conditions or ethanolic conditions? Obviously when it's aqueous conditions. So this is partial positive, this fella is partial negative, right here. Now the OH minus is going to attack this carbon right here. The CBr bond is going to break heterolytically. Why does it break heterolytically? Guys, Sadia, heterolytic fission, if you're confused about that, that's concerning. This is very basic concept of organic chemistry. You can watch my lectures onto YouTube. It's present, heterolytic fission, homolytic. Heterolytic means that the bond does not break evenly. So Why does the bond not break evenly? Because the shared pair of electrons lie closer towards the Br atom. Why do they lie closer towards the Br atom? The reason why they lie closer towards the Br atom is because Br is more electronegative than carbon. So the electrons are not shared dead center, rather they lie closer to the Br atom. So if the bond were to break, both the electrons in the bond go towards Br because they already lay closer here, right? So both the electrons go, and that's called heterolytic fission. Homolytic fission happens, Sadia, when the electrons are shared dead center between two atoms. And the reason why that would happen is if there is no electronegativity difference or very, very similar electronegativities of two atoms. And that's why it breaks homolytically, wherein each atom takes one of the electron in the shared pair electron bond, right? So that's the difference. I don't want to go into the details for that now. So the hydroxide ion attacked this carbon right here, and obviously this was my haloalkane, and this is my nucleophile, right? This fella was my nucleophile. And where did this nucleophile come from? This nucleophile came from sodium hydroxide aqueous and heat under reflux, right? So now what happened is the hydroxide ion attacked this fella right here. The CBr bond broke, and what we do is we show a theoretical structure. This is in fact something, this is not an intermediate per se, but this is basically a theoretical structure in which what we do is we tell the examiner that, hey, you have a C bonded to a hydrogen right here and a C bonded to a hydrogen right here, you know, C bonded to another hydrogen, and the C is also bonded to CH3. And we tell the examiner that, hey, the hydroxide ion is going to bond to this carbon and the CBr bond is going to break. So this fella starts to bond to this carbon and this fella starts to break. And we say that this happens simultaneously. And that's why we represent it with dotted lines. We say, hey, the hydroxide ion basically starts to bond with the carbon and the CBr bond starts to break, right? And you guys might start to think right now to yourself that, hey sir, carbon has made 5 bonds here, hasn't it? See, 1 bond, 2 bond, 3 bond, 4 bond, 5 bonds. Is it actually possible to make 5 bonds? Please understand that these are not 5 bonds that carbon is making. Basically what we are saying is, we are saying that carbon has effectively still made 4 bonds. Sir, how do you know it has made 4 bonds? This is 1 bond, that's the other bond, that's the other bond, and by these dotted lines we represent that, hey, carbon has made a bond 50% with the OH. 50% of this bond has formed and 50% of this bond is being broken, right? So effectively it constitutes a single bond. 50% of this fella has formed and 50% of this bond has been broken, and that's why we also add a negative charge here. We also add a negative charge here. Why do we add a negative charge? Because hydroxide ion had a negative charge with it, so this entire fella becomes negative. Now, is this an intermediate? No, it's basically a theoretical structure. You call it an activated complex structure, you call it the, you know, transition state structure, nobody cares. It's just theoretical. And then what we do is we show the final structure, which is in fact that the CBr bond is going to be broken. This CBr bond breaks and you have C bonded to OH, this H, and CH3. So the CBr bond now breaks completely. You end up with C being bonded to a hydrogen, being bonded to another hydrogen, being bonded to CH3, and this fella becomes, you know, obviously, I'm sorry for my pathetic drawing. It's just like hydrogen, this is CH3, and this fella becomes the OH, right here. This is what happens, and the Br ion is as is. Now please pay very attention here. This is the most crucial part in understanding. Yes, NaBr is going to form then, because the bromide ion went and sodium ion is going to react with it and form NaBr. I couldn't care less about this. This is how haloalkane went into an alcohol. Now this is in fact the moment where you understand the concept. Now it's very easy to understand. This was a primary alcohol, right? A primary haloalkane. And a primary haloalkane will always make a primary alcohol. See, primary haloalkane made a primary alcohol. Great stuff. Always have these connections in your brain. Now, one thing to understand is this the SN1 mechanism or is this the SN2 mechanism? That's what you need to understand. I've never learned it. Let me teach you the basic idea. The basic idea is SN1 mechanism meant that it is substitution, it's nucleophilic, and it's unimolecular. SN2 means that it's substitution, it's nucleophilic substitution, and 2 means it is bimolecular. Bimolecular means there are 2 reagents, 2 molecules or 2 reagents or 2 reactants involved in the rate determining step, which is the slow step. Sir, what do we mean by this? What we mean by this is, let's look at our example. Our example has the sodium hydroxide, it has the hydroxide ions being involved, and it has the haloalkane being involved, right? So what you realize is that if you want to talk about the rate of this particular reaction, what is going to determine the rate of this particular reaction? Since in the first step, there are two reagents involved. Look at this. There's the hydroxide ion is also involved in the first step. So if you increase hydroxide ions, rate is going to increase. If you increase the concentration of haloalkanes, the rate is going to increase, because it's the haloalkanes which are involved in the first step, and it's also the hydroxide ions which are involved in the first step, which is also the rate determining step, right? Because through this first reaction, how quick this first step is effectively how quick the alcohol is going to be made. So how do you determine how quick this first step is? You can either add a lot of hydroxide ions, or you can add a lot of haloalkanes. You can increase the concentration of hydroxide ions and haloalkanes, and you're going to have a higher rate of reaction, right? It's because if this step is quick, then alcohols will form very, very quickly, right? So you understand that there are two reagents involved in determining the rate. In the first step, there are two reagents involved, and that's why these two reagents are the fellas which will determine the rate. And whenever two reagents determine the rate of a particular reaction, it's called SN2 mechanism, because see, SN2 means bimolecular. There are two reagents involved in the rate determining step. And see, the first step, in this case, there's only a single step, right? It's just the first step right here. This is just a theoretical structure. It happens in a single step. This reaction mechanism takes place in a single step. So effectively, this first step is the rate determining step, because it's the only step that happens. This is just a theoretical structure. So this happens, and then a product forms right here. So you understand that since there are two reagents involved, two molecules involved in determining the rate, that's why it's called SN2 mechanism. And that's the reason why primary alcohols undergo SN2 mechanism. That's all. See how easy is this? How easy is this? Easy. Now, let's also discuss another SN2 mechanism. And see, this is, if you want to see the graph for it, this is just a single step right here. Just a single step. That's all. Right? This is how it'll happen. Done and dusted. Now, let's discuss the second mechanism. SN2, the same, I'm not going to write which fella is it, but this is how haloalkanes went into alcohols, right? And primary haloalkanes will make primary alcohols. This is done now. This mechanism is done. And we've done it through the SN2 mechanism as of now. And we know that SN2 mechanism happens from primary alcohols, and it's just a single step. The other fella, the middle step, is just a theoretical structure. So it's effectively just a single step. Right? Now, let's discuss haloalkanes going into nitriles, because see, only these two mechanisms are part of Cambridge International course. This mechanism, haloalkanes going into amines, it's not part of your course, but I'll still teach it to you. The mechanism isn't part of your course. Only these two mechanisms are part of your course. So let's discuss nitriles here. We are using sodium cyanide in ethanol, and we are heating or heat under reflux. Now, what happens? How does it happen? Let's discuss it. We'll take the same haloalkane, which is CH3, bonded to a carbon, bonded to a hydrogen, bonded to another hydrogen, and this is the Br, right? Now, if I'm using sodium cyanide, I know that the cyanide ion is effectively my nucleophile. And remember, it's the lone pair on the carbon which will attack this partial positive carbon right here. There's a reason to it. I don't want to go into the detail, but remember, it is the lone pair of the carbon which is going to attack, not the nitrogen's lone pair. It's the carbon's lone pair which is going to attack this partial positive carbon. So effectively, what's going to happen? This fella is going to attack this carbon right here. We know that the CBr bond is going to break heterolytically. You're going to end up with a theoretical structure that looks something like this, which is C being bonded to H, being bonded to, partially bonded to Br atom. 50% of this bond broke, 50% of the CN bond formed. This is my CH3, this is my hydrogen, nobody cares. This is the negative charge on it due to the cyanide ion, and now the CBr bond breaks completely, and you end up with what? You end up with C being bonded to a hydrogen, being bonded to a CH3 right here, you know, a hydrogen and a CH3. All right, show CH3 right here. This is hydrogen. Sorry for my pathetic drawing. I just couldn't care less. And this is a CN being bonded. And this fella is effectively your nitrile. When a CN is bonded to a carbon, this fella becomes a nitrile, and the Br ion went away. Right? The CBr bond broke. I know that this drawing is not perfect, but I'm trying to make it a little better. चलो कुछ ना कुछ बना ही दिया. But this is how you form nitriles. This fella is called nitrile. And what is the name for it? See, if you want to name it, you start numbering, right? So 1, 2, 3, 1, 2, 3, right? So it's called propane. There's 3 carbons involved. It's called propane nitrile. The naming for nitriles aren't part of your course, but hey, this is called propane nitrile. Done. This is what nitriles are. Now, why are nitriles important for us? We're going to talk about that in a moment. But before we do, can you guys tell me, is this the SN1 mechanism or is this the SN2 mechanism? Never ever be confused by these shortcuts. Don't use shortcuts in SN1 and SN2. Ki primary hoga to it's a single. No. To keep things very crystal clear, I have never learned this. Remember, you guys are going to now tell me, is this SN1 or SN2? Sir, how does carbon have the lone pair? Faizan, it just has the lone pair. Because see, carbon is bonded to 3 it has made a triple bond with nitrogen, and because carbon is in group 4, it has 1 electron that is right here, and 1 electron comes from the outside, and it therefore becomes a CN1 minus sign. Happy? That's how it becomes CN1 minus, and that's why the lone pair of carbon attacks it. Happy now, Faizan? Now you guys tell me, is it SN1 or SN2? Achha, I'll open the everyone chat because I can't click on everybody's icon right here. I've opened the everybody chat. Everyone chat, right? So, SN1, SN2, everybody's correct. Awesome. Now, if I ask you as a student, if I ask you why is this SN2, do you have a reasoning to it? See, a lot of teachers will make you learn this, but there's reasoning to it. It's called SN2 because number 1, it's a nucleophile involved, so nucleophilic substitution because the CBR bond. And why is it 2? Because see, it's bimolecular. In the first step, which is the rate determining step, which is the slow step, the first step, which is the rate determining step, it's also called the slow step. There are 2 fellas involved. There are 2 reagents involved in the rate determining step. And that's why it's called SN2 mechanism, bimolecular. So why is the rate determining step the slow step? So Shahir, again, I don't want to go into the details for it, but if you want to know, I'll tell you. Thoda sa, again, this is not like a proper full-fledged class. I have to finish off things. Sir, why wasn't it called NS? I don't know, Michelle. You have to ask IUPAC this. But I'll tell you why is the rate determining step the slow step. For example, since I'm also a finance guy, I worked in industries as well, auditing these industries. Let me tell you something. Let me just use my industrial knowledge to explain the rate determining step. Why is rate determining step a slow step? Because understand, let's suppose you work in Pepsi Coca-Cola factory and you make 1 bottle in 1 hour, right? You make 1 bottle in 1 hour. Who asked this question? Shahir asked, right? So Shahir, let's suppose you make a single bottle in 1 hour and then you fill that bottle up in 5 seconds. Now you tell me, how many bottles will you make in or let's say 1 minute kar lete hain. How many bottles will you be able to make in 3 minutes? How many bottles of how many Cokes will you have filled in 3 minutes? How many Coca-Cola bottles would you have filled in 3 minutes? 36 bottles. Okay. How many Coke bottles would you have filled in 3 minutes? 2. How 2? If it takes you 1 minute to make a bottle and it takes you 5 seconds to fill a bottle. Now, a lot of you guys are using the 5-second idea. Ki, oh, sir, if it takes you 5 seconds to fill a bottle, then in a single minute, there are 60 seconds. 60 divided by 5, that gives me 12. So 12 plus 12 plus 12, that's 36. That's absolutely incorrect. You can only make 3 filled bottles. Why? Because it'll take you 1 minute to make a Coca-Cola bottle. That's basically the slower step. So you can't, fill out 36 bottles if it takes you 1 minute to make a single bottle, right? So in total, you would have filled out 3 bottles, not 2, 3. In 3 minutes, if it takes you 1 minute to make a single bottle, then in 3 minutes, you would have made 3 bottles and then filled it up in 5 seconds and you would end up with 3 bottles, right? Acha yaar, please don't use technical word. Yaar, if 3 minutes, acha, 3.5 minutes. Happy now? Ab 3 bottles ho gaye. Some people are saying it'll take it 5 seconds, so only 2 bottles. So 3.5 minutes. Happy now? Acha, happy. No, this process takes place simultaneously. Right? Understand this. So there's a machine involved here and there's a machine involved here. Now, obviously, have you not seen how industries work? So there are 2 machines involved. Right? So you realize that no matter how quickly you can fill this up, you realize that, hey, because you're making bottles load, let's suppose I give you a car example. You make one car, you make the engine of a car, let's suppose in 50 days. And you assemble the car, the entire car, everything else in 1 hour. How many cars can you make in 1 hour? 0 cars. Why? Because it will take you 50 days to make the engine. That is the reason why I said that the slow step is the rate determining step. Now got it, Shahir? Right? So if there are 4 people involved, yes, you got it? If there are 4 people involved and there's like a chain reaction that is going to take place. If one person it's like a relay race. Think about it like this. It's like a relay race. No matter how quick one of the guy runs, if the first fella runs very slow, he's going to determine your rate. Right? So got it. Great. Now I don't want to go into more technicalities for it. Great. So this is the SN2 mechanism. And we're also done with this part. This is how nitriles form. Now again, amines aren't part of my course. The mechanism for amines aren't part of my course. So I don't want to go into their detail as of now. Right? As of now, I don't want to go into the detail for it. Okay? I'm going to discuss it once I'm done with all of this. Now, why are these nitriles very important? These nitriles are very important is because the moment these nitrile forms, I think it is reaction 13, if I'm not wrong, in our mind map. It's reaction 13 in the mind map. Yeah, see right here. The moment these nitriles form, we do something to it. What we do is we perform hydrolysis. We add water to it. And we add water to it in the form of an acid. So we add water either in the form of acid or in the form of alkali to it. And that's basically what hydrolysis is. So we hydrolyze this particular, where did it go? We hydrolyze this particular fella right here. And how do you hydrolyze it? You either add dilute acid. Normally we either add dilute hydrochloric acid or dilute sulfuric acid, or you can also add dilute alkali to it. So you can add dilute acid or dilute alkali to it. It hydrolyzes into carboxylic acid. So instead of the CN, now you just end up with COOH. Right? And why is this important for us? Because notice how by converting it into a nitrile, we increased the number of carbon by 1. So previously we only had 2 carbons, and this is what will help you a lot in organic synthesis. You had 2 carbons, but the carboxylic acid that has formed has 3 carbons, which means that the intermediate was you converted it into a nitrile first. Because it is that when you convert it into a nitrile, that is when you increase the length of the chain by 1 carbon. See, here you had 2 carbons, and in the final product, if I tell you that, hey, you had a haloalkane and it became a carboxylic acid, and the carboxylic acid has 3 carbons, you automatically realize that, hey, from 2 carbons, if the carboxylic acid has 3 carbons, in the middle steps, what would have taken place is you would have first converted it to a nitrile, and then you would have hydrolyzed the nitrile. Because once you perform the hydrolysis of a nitrile, you end up with carboxylic acids, right? So this fella is called a carboxylic acid. And nitriles, write it with yourself that nitriles increase the number of carbon by 1. So nitriles always increase carbon number by 1. Done, guys? And if you use dilute alkali, you can also form the acid from it. How? When you use dilute alkali, you first end up with a salt, because you know that when an acid forms, it can react with the alkali to form a salt, right? The carboxylate salt. So it can end up with COO minus, and this is the Na plus, right? This is the salt which forms. So if you add dilute alkali to it, the carboxylic acid forms, but since it's alkali as well, you know, the nitrile hydrolyzes to form acid, and because alkali is also present, let's suppose I add sodium hydroxide. If the alkali is present, then the acid is going to further react with the alkali and form this salt right here. The sodium ion is going to now be bonded right here. And so if you want the carboxylic acid, you further acidify this. You further add dilute acid. So at the end of the day, if you want to end up with the acid, you have to use dilute acid. But if you use dilute alkali, then you further acidify it. And by the way, this is going to be an acid-base reaction. By the way, so when you further acidify this fella, you end up with the same thing. You end up with a carboxylic acid right here. The same thing, right? So you could hydrolyze it by using dilute alkali, and you will end up with a salt, but you could further acidify the salt to get carboxylic acid. Or what you could do is you could just use dilute acid and end up with carboxylic acids. Done? Please use the everyone chat. Thank you, guys. Thank you. I know it's easy. Sir, the way you do it is so simple. I know it's simple. I know. Right? Achha. Next. Now, this is two mechanisms which are done through the SN1 pathway, and it's a single step mechanism. Now, I'm going to write a tertiary haloalkene. I'm going to form a tertiary haloalkene now. Same Br, right? And this is partial positive carbon, and this is partial negative Br, because there's electronegativity difference between the two, separation of charge. Now I'm going to use a hydroxide ion right here, right? And it's obviously sodium hydroxide in aqueous solution and heat under reflux. Now, what's going to happen, everybody? What's going to happen? What's going to happen? Now, you guys might think, hey sir, the hydroxide ion will now behave as a nucleophile, and the hydroxide ion is going to attack this partial positive carbon right here, and this bond is going to break simultaneously. Isn't that true? Everybody should think like this. Shouldn't everybody think like this? Absolutely. If you have no idea about organic chemistry as of now, everybody should start to think like this. Oh no, you dumbo jumbo. Don't think like this. Do you know why? Because although the hydroxide ion can behave as a nucleophile, the problem is there are three alkyl groups involved here. And the three alkyl groups are so large, they are large enough to cause something known as steric hindrance. What is steric hindrance? Steric hindrance is basically because these atoms, these groups are so large, it prevents the hydroxide ion to be able to attack this partial positive carbon. Right? So effectively, this hydroxide ion, it constitutes useless for us. It's useless because although this fella will want to attack the partial positive carbon right here, it can't absolutely attack it. Why? It can't attack it effectively. Why? Because it has been surrounded by these three large alkyl groups, which causes something known as steric hindrance, which is, but just for now, understand that steric hindrance is basically because of these large alkyl groups, there's something known as steric hindrance, which basically means that the alkyl groups prevent the hydroxide ion from attacking this partial positive carbon since they are large. They say traffic, it's like a traffic jam. You want to reach from point A to point B, and there are a lot of cars in between. Think of these CH3s as a lot of cars in between. So you won't be able to reach point A to point B because of these a lot of cars here, right? But if it's a primary haloalkane, then you are able to reach it because there's no steric hindrance or less steric hindrance, right? So you're able to, there's just one car in between, so you're able to navigate your way and reach point B. But this fella is useless for me. Now, if this fella is useless, this part wouldn't happen, but this part would still happen, right? The CBr bond would effectively break, wouldn't it? The CBr bond would effectively break. Although this is not going to happen, but the CBr bond slowly and gradually, it's going to start to break. And it does break. So when it breaks, you end up with a carbocation intermediate. This breaks heterolytically and you end up with a carbocation intermediate right here. And also notice how beautifully the tertiary carbocation intermediate is more stable. It's a tertiary carbocation intermediate which forms. And this also is, a further evidence for you guys. A tertiary carbocation intermediate would form. Therefore, this fella, number one, why is, if this is a tertiary haloalkane, it favors the other pathway. Why does it favor the other pathway? It's because number one, there's steric hindrance involved, and number two is tertiary carbocation intermediate would form, which is more stable, and that's why this pathway is preferred. It's energetically favorable. And then what's going to happen? The hydroxide ion is going to be present. And okay, here a lot of students have another confusion. A lot of students say, sir, the hydroxide ion is present, you are right, but there's also the bromide ion present. So wouldn't the bromide ion again attack this carbocation intermediate? The answer is no. Why? Because the bromide ion, if it's present in a solution and hydroxide ion is present in a solution, hydroxide ion is a stronger nucleophile compared to the bromide ion. So it's the hydroxide ion which is going to attack this positive carbon right here. This carbocation intermediate, and you're going to end up with what? You're going to end up with a tertiary alcohol. So a tertiary haloalkane will give you a tertiary alcohol. A primary haloalkane is going to give you a primary alcohol. And by the way, what is the name for this mechanism? Is this SN1 or is this SN2? And see, this is two-step mechanism. This was the first step and this is the second step. So it's a two-step mechanism, and because obviously the first step is the rate determining step, it's the slower step. What do you call it? You call it SN1. Why SN1? Because if you go back into the definition for SN1, see, this is how beautiful chemistry is. If you go back into the definition of SN1, S means substitution, N means nucleophilic, 1 means it's unimolecular, which means a single reactant is involved in determining the rate. It is involved in the slower step. A single reagent determines the rate. A single reagent is involved in the rate determining step. And that is true. Even though the hydroxide ion is present here, it is useless. Why is it useless? Because of steric hindrance. So it's only the concentration of haloalkanes which will determine the rate of the reaction for this fella. And that's why tertiary haloalkanes, because of steric hindrance, will undergo the SN1 mechanism, because it's only a single haloalkane which is responsible for the rate determining step. The hydroxide ion constitutes useless for us. Just like in SN2, the hydroxide ion was useful for us because, see, or even the cyanide ion was useful for us because this was also attacking. So since both the fellas are involved in determining the rate, it was called bimolecular. But in the first case, in this particular case right here, it's only the haloalkane which is involved in determining the rate in the slower step. That's why it is called unimolecular SN1. Easy, guys. That's why, Aisha, it takes some time. It takes some time to break the CBr bond. It's the slower step, right? That's why it takes some time. Aisha Singh said, aren't the alkyl groups gonna try to stabilize this partial positive carbons? They're trying to do that because alkyl groups are electron donating. They have the positive inductive effect. And that's why this is the slower step, Aisha. It takes some time to do that, right? And so that's done. This is how you know the difference between SN1 and SN2. Now, can you guys tell me which mechanism? Can you guys write the mechanism for yourself? And you guys also tell me, would it undergo SN1 or SN2? And can you guys basically write the mechanism as well? You know, look at this. Now, if your concept is crystal clear, it's going to be a piece of cake for you. You would know whether it's SN1 or SN2. Always think from the perspective of a rate determining step. How many reagents are involved in determining the rate? Sir, our teachers have not taught us like this. I swear to God, you are so... thank you. Movies is saying, sir, miss your clean shave era. I'll clean shave again. Okay, so this is going to be SN1. Why? Because the moment this fella would want to attack this guy, it wouldn't, because there would be steric hindrance. So it's only a single fella which is involved in determining the rate, and that's the reason why it's going to be called the SN1 pathway. And so a tertiary carbocation intermediate is also going to form. And see, that's favorable. Tertiary carbocation intermediate is in fact favorable for us. The CN is right here. And it's going to attack this guy. Curly arrows. Curly arrows basically represent the movement of electrons. And this is how a nitrile is going to form. And this nitrile can be further hydrolyzed. This nitrile has increased the number of carbon. You can further add dilute acid to it or dilute alkali, and it's be hydrolyzed into carboxylic acid. So this fella is going to give you, instead of CN, it's going to now be COOH. So screenshot time. Okay. So these are the two mechanisms. Acha, see, in my live classes, I've discussed everything, how the shape changes. You go from tetrahedral shape to trigonal planar shape and then back to tetrahedral shape. I'm not concerned about any of that. So again, explanation is going to be difficult, Muhammad. Sir, do we mention steric hindrances past paper questions? Yes, you do. But in the past paper questions, you are never asked as to why the tertiary haloalkanes are going to undergo the SN1 mechanism and why they are going to undergo the SN2. That is the reason why primary would undergo SN2. That is the reason why teachers make pathetic bullshit explanations to it. Because it's not going to be tested in the exam. Here you go. One screenshot. Sir, please conduct past paper session. I'll try, Hajra. If I have the time, I'll do it. But I'm already doing a lot of topic-wise questions with my students. No, Michelle, I never said that. Please don't put words in my mouth. I never said that. Michelle, Michelle, galat. Michelle is saying earlier you said that all carbocation intermediates have the same stability. I never said that, Michelle. Rewind, watch it again. I said that haloalkanes are equally stable. Carbocations equally stable तो नहीं होती ना. Tertiary carbocations are more stable than secondary, which are more stable than primary due to the positive alkyl. In the last class we discussed all of the stability of carbocation intermediate. क्या हो गया Michelle? Yeah, don't confuse it please. Don't confuse it. अच्छा. Sir, please also do the NH3 mechanism. Again, this mechanism isn't part of your course, but if you want to know the the NH3 wala mechanism, let me show it to you. You guys can take a screenshot here as well, and then I'm going to show you guys the amine. How do you go from what's it called? From haloalkanes into amines, right? Done? Okay, now let me explain the haloalkanes into amines idea. Chalo. Let's take the same CH3, Br, hydrogen, and hydrogen, let's suppose, right? Now what's going to happen is, if you have NH3, excess NH3, again, this fella is a nucleophile, right? And let me show it to you like this. NH3, this fella is a nucleophile, right? Now this is again partial positive carbon, partial negative Br. This fella is going to attack this carbon right here. The CBr bond is going to break heterolytically. It's SN1 mechanism that's taking place right here because it's a SN2 mechanism that's taking place because it's a primary haloalkane, right? It's only bonded to one alkyl groups. Two fellas are involved in the rate determining step. Now, what's going to happen? Sir, so from for secondary haloalkanes, it depends. Normally, secondary haloalkanes also undergo the SN1 mechanism, but you also understand that normally they undergo SN1, but you can also equally undergo SN2. So understand that for secondary haloalkanes, you are not going to be tested, and if you are tested on secondary haloalkanes, they'll tell you which mechanism it's taking, and then you draw that mechanism for it. Sir, I meant whether SN1 is favorable for trigonal planar or SN2. I don't know what that means. Sir, this is a tetrahedral shape, so what if it was a trigonal planar shape? If it were a trigonal planar shape, then it would mean that there's a carbon-carbon double bond. What are you trying to say, kiddo? I am not understanding, Aisha, your question. Sir, when do we use HCN and KCN? We're going to talk about that, Hadia, in a moment. That's when you have ketones and aldehydes, right? Nucleophilic addition reaction mechanisms, Hadia. Acha khair, let me just quickly talk about this. So although this is not going to be tested since this is a little complicated, but the moment the CBr bond is going to break, we're going to show this as 50%, just like we do. We're going to show this as 50% formed and 50% broken. I'm just showing you guys the NH3 bonds because that's going to help me basically talk about what's going to happen next, right? And these are the two hydrogens, by the way. So this fella broke, and obviously what charge do you have? Do you have any charge? You have no charge right here. Why? Because see, the NH3 has no charge on it. So there's no charge here as well, unlike the hydroxide ions and the cyanide ions. This is basically the transition state, which is a theoretical structure that I'm going to form. Now what's going to happen? The CBr bond is going to break, right? The CBr bond breaks, and the moment the CBr bond breaks, since both the electrons go to the Br, this entire fella becomes positive, right? This entire fella has a positive charge. Even you could say the nitrogen has effectively ends up having a positive charge. So what happens is the CBr bond broke, and you have N bonded to 3 hydrogens. I'm just simplifying this, right? And there's going to be a positive charge right here. Now, what further happens is, because there's a positive charge on nitrogen, and nitrogen is very, very, very electronegative, it's one of the 3 most electronegative elements on the face of planet Earth, it does not want to have this positive charge on it. It wants to have, it does not want to have any positive charge on it. It says, hey, take away the positive charge. And so what happens is, one of the NH bonds must break now. And now, how does one of the NH bond break? The NH bond breaks because since you have excess ammonia, that's why we use excess ammonia, because if you have excess ammonia, you're going to have excess NH3 molecules, and the moment this fella forms, since this end does not want to have a positive charge, it says, okay, I'm going to help you not have a positive charge. This ammonia attacks this hydrogen right here, and the hydrogen, the NH bond, it breaks heterolytically, and both the electrons go towards this nitrogen. So what ends up forming is ammonium ion forms. Right here, see, the ammonium ion has formed. The NH3 ended up taking the hydrogen ion, so forming the ammonium ion. And since you also had the bromide ion in the solution now, ammonium bromide actually ends up forming. So NH4Br forms, and you end up with C bonded to CH3 bonded to two hydrogens and bonded to NH2. This is what happens. There's a reason to it as to why this fella ended up having a positive charge. There's a reason to it. It has to do with dative bonds, and when the CBr bond broke, both the electrons went to the Br, then this forms a dative bond here. Both the electrons are donated by nitrogen and ends up forming the positive charge, but nobody cares. Just take my word for it. Done. Achha, this positive charge, because see, it accepted a hydrogen ion. There's a dative bond between NH3 and H, ends up with ammonium ion and bromine. Done. And so Cambridge Examiner says that the byproduct is HBr. That's absolutely incorrect. The byproduct is ammonium bromide. Please understand this. Write it with yourself if possible. And you can see it in Pearson books as well. And this mechanism, by the way, is not part of your course. This mechanism is not part of your course. But the equation can be tested. The equation can be tested. What was the equation? You have CH3, CH2Br. So you have CH3, CH2Br. And if you add excess ammonia to it and heat it, and ammonia is a gas, that's why you heat it under high pressure in a sealed tube. And so if it reacts with NH3, you just need to know that when NH3 reacts here, ammonium bromide is going to form, and this will be CH3, CH2, and NH2. That's all. So instead of the Br, you end up with NH2. Now, why is it not NH3? You know why it's not NH3, because you now also know the mechanism for it. So there's no rote learning to it. It's CH3, CH2, and the new thing that has been bonded is NH2. And this fella is called amine, which you'll study more of in A2 chemistry. And you end up with ammonium bromide right here. Done. And obviously this is 2NH3 if you were to balance it. Sir, in the exams, will we write HBr or NH4Br? You will write ammonium bromide, but it's not going to be tested. So just like when you were talking about NaOH, where they make us write the wrong product, which is HBr, instead it is H2O and NaBr, absolutely. Absolutely. Hi, Sara. Absolutely. Because I'll tell you why Cambridge does it, Faizan. Cambridge does it because Cambridge knows that the mechanisms aren't part of your course. But what it ends up doing is it ruins students' concepts. So these two mechanisms, since it weren't part of your course, Cambridge just simplifies it and says HBr and H2O is the byproduct, or in this case, HBr is the byproduct. But it's the reality of the thing is that ammonium bromide is the byproduct, sodium bromide and H2O is the byproduct in the above case scenario, right? Will Cambridge test it? No, Cambridge never tests the byproduct. Cambridge never tests the byproduct. You can even check. He gives you the byproduct at times. He says this is the byproduct, this is the byproduct, but he will never test it. Yes, this is the same. Sir, Sardar is saying you aren't young and you are as old as him. Sir, Sardar बुड्ढे बनने हैं, मुझे बुड्ढा बना रहे हैं. Sir, Sardar को मैं खुद बुड्ढे हैं, मैं नहीं हूँ बुड्ढा. Khair, I'm very young, very young. Khair, this is the idea. This is the idea of the last mechanism. So we are done. And the last mechanism isn't part of your course, but we are done. Now, also one more thing to understand, we're done with all three, right? So if I were to effectively go back to my mind map, and I also want to discuss one more thing. If I were to go into my mind map, how do you end up with haloalkenes into amines? You use sodium cyanide or potassium cyanide, and this must be ethanolic, dissolved in ethanol, and you heat under reflux. Now, why should it be dissolved in ethanol? Why should it be dissolved in ethanol? Because understand, if it is dissolved in if it's not dissolved in ethanol, and if it's aqueous would mean you also have the hydroxide ion, and hydroxide ions are better nucleophiles than any of these fellas. So there's a possibility that the hydroxide ion would attack the haloalkenes and then form alcohols. Yes, sorry, amine ki baat karu. Sorry, I have right here. Right here, this is NaCN. I wrote it in the incorrect area. Nitrile में लिखना था ना. NaCN in ethanol. My bad. Yeah, thank you for reminding. And this is heat under reflux. Thank you. Yes, thank you. This fella is what? It's NH3, excess NH3 or conc NH3 in a sealed tube. Heat in a sealed tube under high pressures. Done. And last but not least, and this fella, we studied nitriles to carboxylic acid. It's what? it is dilute acid. Or if you use dilute alkali, then you have to further acidify it, right? So dilute alkali, and this is called hydrolysis, by the way. This is hydrolysis, and the above three, all three are nucleophilic substitution reaction. Dilute alkali will form the salt first, and then acid-base reaction takes place, and the salt ends up forming the acid again. And how? By adding dilute acid here again. Normally you either use HCl or you use H2SO4. And what was the other reaction? Right here. Sodium hydroxide, ethanolic, heat and reflux, alkenes. एक और reaction था. So haloalkenes to alcohols. How? Again, the same sodium hydroxide. See, in these both cases, sodium hydroxide, but one is ethanolic and one is aqueous. And then you heat under reflux. Remember, NaCN must be dissolved in ethanol, because if it's aqueous, there's a possibility that the hydroxide ion acts as a nucleophile and it ends up making an alcohol. So you have to prevent that. Done. Haloalkenes are officially over. But I want to discuss something. I know I shouldn't be discussing it. I've already discussed everything in my life class. This is just a summary. But since a lot of students are here, they're depending on me. So I'll just quickly discuss that as well. I'll quickly discuss that. What do you want to discuss? Dekhiye. If you have a tertiary haloalkane and a primary haloalkane, they're equally stable. But understand that a tertiary haloalkane has a faster rate of reaction. It has a much quicker rate of reaction. And the reason is because of the alkyl groups. Because in tertiary haloalkenes, you have alkyl groups which are electron donating, and they are electron donating, they have a positive inductive effect, and that is the reason why they push electrons towards the and ends up towards the carbon, and ends up concentrating the negative charge on between the CBr bond, and the CBr bond breaks heterolytically. And so so you realize that the tertiary haloalkenes, they are going to have a faster rate of reaction than the primary haloalkenes. This is one thing to understand. Yeah, it is counterintuitive, Faizan, but it's also you need to understand that जो बात मैंने की है ना कि stability of haloalkenes की जब मैं बात कर रहा था, I said it for a reason, because it's been tested multiple times in the exam, Faizan, and students, they tend to confuse it with the stability of carbocation intermediate. I know it may look confusing to you as of now, but when you study, probably when you're in the third year of university and you're studying organic chemistry, you'll realize why I said what I said. Just like why when we lie in O-level and IGCSE. So it's effectively lies. Sir, Allah na kare. Khair, but tertiary haloalkenes, they normally have a faster rate of reaction compared to primary haloalkenes, right? Tertiary compared to primary. Now, one more thing to understand is the fact that it's not always this case. This is not always the case. Why is this not always the case? It's because if you take a tertiary haloalkane and you make it undergo the SN1 mechanism, and you make the primary haloalkane undergo the SN2 mechanism, which is energetically favorable for both, this fella wins. This fella has a higher rate of reaction. But you also understand is that you can force the tertiary haloalkane to undergo the SN2 mechanism. You can force the primary haloalkane to undergo the SN1 mechanism. You can absolutely do that by providing it with energy. Right? You can do it. You can make it. You can force it. Sar pakad ke na isko SN2 karao aur isko SN1 karao. Now, if that's the case, I'm going to have to ask you. I'm going to give you two graphs right here. Just two graphs. Sorry for my pathetic drawing. I'm sorry. But I'm going to give you two graphs. And both these graphs are of SN2 mechanism, because SN2 mechanism is a single step mechanism. SN2 mechanism is a single step mechanism, isn't it? Right? The one structure that exists in between is just a theoretical structure. So now you guys have to tell me which one is a primary haloalkane and which one is a tertiary haloalkane. Secondary haloalkane can undergo either or. The examiner will always tell you. Yeah, you guys tell me. Shabash. Try, think. Dekhiye, I have, in this case, one is going to undergo the SN1, one is going to undergo the SN2 mechanism on their own, and one is going to undergo the SN2 mechanism because you forced it. So if you forced a tertiary haloalkane to undergo SN2 mechanism, it's going to be less energetically favorable. How do you force it? You force it by providing it with energy. So this fella is obviously a tertiary haloalkane. Why? Because see, the activation energy is pretty high. You are forcing it. So you are going to have to provide it with the energy. And this fella is the primary haloalkane. So never confuse this. this, Yeah, it's primary, because primary favor the SN2 mechanism. If you were to perform SN2 mechanism and there's a primary as well as a tertiary, primary will have a lower activation energy because that's more favorable for it energetically. But then if I were to have the SN1 mechanism, and I make sure that SN1 mechanism is two-step mechanism, obviously, because this is the carbocation intermediate which forms, and this is the final product. This is the reactants. This is the EA of the first step, and this is the EA of the second step. The first step is the slower step, right? Now you guys tell me, if I have this and then the second graph looks something like this. Yeah, you guys have to tell me which one is primary haloalkene and which one is tertiary haloalkene. Yeah. Oh my God, it's not fast. Now understand, see, if you make both the fellas undergo the SN1 mechanism, you realize that tertiary haloalkenes are favored in the SN1 mechanism. Therefore, they should have the lower activation energy. So this EA, the green EA, this is tertiary haloalkenes, and the yellow EA, this is primary haloalkenes. And this MCQ is tested in a lot of time, in a lot of detail every single time. No, Hiba is right. Hiba is saying, sir, what if, Hiba is a beautiful question, what if, sir, but you're using sodium cyanide to form a nitrile, wouldn't it cause elimination reaction? No, it would not cause an elimination reaction because you don't have the hydroxide ion. It would cause, it would cause elimination reaction and form alkenes if it was sodium hydroxide dissolved in ethanol, because it's the hydroxide ion which could act as a base and a nucleophile. Sir, I want to join your crash course. Are these recordings available? Yes, everything is available, Michelle. You just contact Miss Naiba, message me or contact Miss Naiba. I'll send you Miss Naiba's contact and then she'll guide you. All recording. There are 134 recordings available along with a lot of practice. I'm the only teacher, I think, who does a lot of practice with students, especially when it comes to A levels. Because in A levels, teachers, they just teach concepts and right? So practice is very important. I've done a lot of practice and I'll continue to do a lot of practice. After I'm done with this marathon, for organic chemistry, I'm going to do a lot of practice. Done, guys? Any questions up until now? कोई सवाल, कोई शक, कोई शुबा? Sir, do you teach A2? I don't. ये ASP जो ना, these students have forced me to teach AS. I did not even want to teach AS because I don't have time. I swear I don't have time. Yeah. So haloalkenes are effective. Let's see if I get the time to teach A2. Yeah. Currently I don't have time. अभी तक तो नहीं है टाइम. जब होगा पढ़ा लूँगा. कोई बड़ी बात तो है नहीं. Sir, you've not shown the hydration mechanism for alkenes. That's not part of your course. The only mechanism that is part of your course when it comes to alkenes is the alkenes going into haloalkenes, either by adding chlorine or bromine or adding a hydrohalogen, which is HCl or HBr. If you want to know that stuff, I can also teach it to you. It's good to know a lot of things, but I can also teach it to you. This right here, this is an alkene. The hydration. Somebody saying, sir, teach the hydration mechanism. Again, why do you need to know all these mechanisms if it's not part of your course? Not part of your course, but if you want to know it, sure. What happens is if I'm using concentrated acid, if I'm using, see, these were the conditions for it. Either you use, what's it called? Either you use steam, H2O gas, temperature of 300 degrees Celsius, 60 atmospheres pressure, and you use dilute phosphoric acid or any dilute acid, not conc, dilute acid, right? Phosphoric acid, acidified phosphoric acid, or acidified sulfuric acid. And what you realize is, hey, the acid acts as a catalyst. So I'll simplify it for you. This is the simplified version. The acid gives a proton. It's a proton donor. The pi electrons attack this proton. The bond breaks. You end up with C being bonded to hydrogen, being bonded to another hydrogen, being bonded to another hydrogen. This fella becomes the intermediate. This fella is then attacked by steam, which is H2O gas. So H2O gas, H bonded to two H's bonded to an O. This fella is gonna attack this carbocation intermediate, and once it does that, because oxygen does not like to make 3 bonds. We know oxygen makes 2 bonds. So the moment it makes a bond here, one of the OH bond must break, and it gives back the lone pair. So one of the bond breaks, gives back the lone pair. You end up with CH3 being bonded to C, being bonded to H, and this is obviously OH which comes here, and the hydrogen ion is liberated again. That's why the acid is effectively a catalyst. Nobody cares, guys. Nobody cares about these mechanisms because this isn't part of your course. So how do you force SN2 to SN1? Energy. No. Energy. So did you have accounting in A levels? No, I had sciences in A levels. So why is the rate of tertiary more faster generically? It's faster when it comes to reaction kinetics. When it comes to reaction kinetics, you understand that it has to do with carbocation intermediate stages. And tertiary haloalkenes ka jo hai na, it's the since there are 3 alkyl groups attached to it, it quickly favors the formation of a carbocation intermediate. But the entire idea of why tertiary haloalkenes have a faster rate of reaction than primary, I've taught it in my live class, but you wouldn't be taught that. Namaz break in 10 minutes, namaz to पढ़ लेनी चाहिए थी. When मैं पूछ रहा था, my dad is leaving ना, he visited me, so he's leaving. I said when he's leaving, let me know, ताकि हम उनसे मिल के वो जाए. Right? So I'm gonna come in a while. You guys, we are done with haloalkenes. If we look at our mind map, this is hydration. Yeah, the alkenes ka hydration and nobody cares, by the way. Ajay, before I go, I've also not taught one mechanism at the start. I'll also teach it right now, right here, the free radical substitution mechanism. In this, first initiation happens where the CL-Cl bond breaks. Let me quickly just go over it. So let's suppose you are dealing with methane, reacts with chlorine, a substitution reaction takes place. You have one chlorine atom being bonded here and HCl forms, right? So CH3Cl plus HCl forms. And obviously what effectively happens is in free radical substitution, initiation first takes place, where the Cl-Cl bond breaks homolytically. Why does it break homolytically? Because there's no electronegativity difference. When you give UV light basically breaks the Cl-Cl bond, and when it breaks the Cl-Cl bond, it breaks homolytically. Each atom takes one of the electron from the shared pair electrons. Since there's no electronegativity difference, the shared electrons lay dead center. So when this bond breaks, it will also be equally getting each of the electrons. So initiation happens wherein chlorine goes and 2 radicals are formed. Radicals are basically reactive species. They are species which are highly reactive with unpaired electrons, right? So you could write it like this, or you could write Cl2 going into a chlorine radical and another chlorine radical. Why am I calling it radical? Because there are 7 electrons in total, unpaired electron hai, right? So this is initiation. In initiation, always remember radicals are going to form, 2 radicals form. Then propagation takes place. In propagation, this chlorine radical is going to eye down a methane fella, and what it does is it basically rips the methane fella of a hydrogen. So it takes the hydrogen. This radical is so reactive that it plucks out a hydrogen and forms HCl, and you end up with a methyl radical. So you end up with a CH3 radical, and this is called propagation, wherein one radical makes another radical, right? And obviously I have done a lot of detail when it comes to initiation, propagation. I've taught you guys why this happens. I show diagram, but that's in the live class. Yaar, isme itna koi badi baat nahi hai. And then the methyl radical again attacks the chlorine molecule and gives you CH3Cl. This is how CH3Cl. See, how does HCl form? In the propagation step. How does CH3Cl form? Again, in the propagation step. Propagation steps are always in a pair, but there can be millions of propagation steps. I've discussed all of them in my live class. It's not relevant for the exam, by the way. Itna relevance nahi hai, propagation, initiation and everything. We have to save time. And again, the chlorine radical forms. And what is termination? When 2 radicals combine and give you a molecule, or when like CH3 radical combines with another CH3 radical, and it can give you butane, it can give you ethane, it can give you whatever, right? So these are termination steps, possible termination steps, possible propagation steps, and whatever. I can teach it in a lot of detail, but since it's neither is it tested nor is it important, that's why बस सही है, इतना काफ़ी है exam के लिए. This is more than enough. If you want to know more about initiation, propagation, termination, how it happens, why it happens, when it happens, कैसे होता है, what's UV light, what are the diagrams you shown, you can see my recordings for it, but it's like wastage of time, right? So I'm gonna go meet my dad because he's leaving, and then said next year teach A2 because AS kids can use YouTube lectures. Sir Suli, I want to take your crash course, but do you think we have time to go over theory? Shouldn't we focus on past papers now? No, Murtaza. In A levels, concepts are more important than past papers, but also understand that there's one more thing. Don't go randomly reading notes, because notes are not going to save you. Because from whatever my experience is, I'll tell you my experience. No teacher teaches A-level chemistry in a coherent manner. They just jump from precipice. If you watch my lectures, I've taught it like a story. Everything falls into place from the first lecture to the end lecture. So if you take those lectures and jot down notes, it will help you guys immensely. But now there's a catch. The catch is, since you're already done with most of your chemistry, when you take my lectures, only take lectures of chapters in which you face difficulty while solving questions. So once you take those lectures, then do topic wise practice. Buy my topical booklet. I've already lost over $500,000 by printing these booklets. Then people did not buy it because it was expensive, but khair, nobody cares. It's for 6,000 rupees or something. आप ये टॉपिकल बुकलेट लें और इसकी मार्किंग स्कीम अवेलेबल है ऑनलाइन, वो आपको इसके साथ मिलती है सॉफ्ट फॉर्म में. बाय दिस टॉपिकल बुकलेट एंड यू कैन मैसेज मी, आई सेंड यू द पर्सनस नंबर. आप इसको बाय करें. इसमें थ्योरी के सवाल करें क्योंकि मैंने खुद कंपाइल की हुई है. ये करें और आराम से चिकें. आई नो 6,000 is costly, but it costed the other person a lot of money. It cost him about 5,000 to make, and then I had to pay him. I paid him $500,000 because students were forcing me to say, "Aap topical booklet." That's why I did not publish the MCQ booklet. You guys are making me lose money, man. Yeah, $500,000 is 5 lakh रुपए. It's not a सही है 5 लाख रुपए. $500,000 की बात नहीं कर रहा, रुपए की बात कर. खुदा का खौफ करें. So we could get the soft form from money and solve it on tablet. That's also true. Khair, on the graph, what's left is, let me go meet my dad. But on the graph, what's left is, we're almost done with everything. See, all of this graph is done. Now we're going to move on to alcohols. That's the next chapter. So now we move on to alcohols. And after alcohols, this is what's left, right? So we are left with alcohols and we are left with carbonyl compounds right here, aldehydes and ketones. And we'll be done with organic chemistry in its entirety. So then I'll also give you guys tips and tricks and all of that good stuff. So we're just left with carbonyl compounds and alcohols, and then you'll be done, right? And then once I'll also do all the mechanism. Sir, whoever's taking your crash course, can you share sir's charges? Michelle, you can just contact Miss Naiba. She will guide you, because a lot of students, they face financial crunches, and nowadays we know in the age of inflation, a lot of students face difficulty paying a hefty amount to these teachers, including me. But Miss Naiba will cater to you. Don't worry. She will devise a payment plan for everybody. She does it. She tells me, sir, मैं कर रही होती हूँ. तो I don't dwell into these administrative matters. ये Miss Naiba करती हैं, Sir Ali करते हैं, Sir Basit करते हैं. But if there's any sort of financial crunch, Miss Naiba will accommodate you. I promise. If she doesn't, you can contact me. फिर मैं लड़ता ही हूँ और मैं क्या करता हूँ, फिर मैं बेइज्जती खा लेता हूँ बाकियों से. मैं लड़ लेता हूँ. क्या कर सकते हैं? But this is my hobby. This is my hobby. The reason why I charge so much is because for my time is expensive and I don't want to give anything out for free, because free की कदर नहीं होती ना. Free बंदा बैठा रहे किधर कदर होती है free चीज़ की. People take you for granted. So there's a value. Now you guys, what you guys can do is, you guys can take screenshots if you want, look at the mind map. I'd suggest looking at the mind map and completing it on your copies, and I'll be back. I'm going to talk to my dad. He's leaving, and I'll be back. Sir, why do you teach at Conceptual Academy? Why not on your own? Because this is my academy. It's my baby. Sir Abbas and I came up with it, and Sir Basit back in 2022. It's been 3 years, 4 years. So I'm going to pause the recording here and I'll be back. आप लोग बैठे हैं, चाय पानी पिए, शरबत पिए, रोज़े तो ऐसे भी आप लोग नहीं रखते हैं, कोई मसला नहीं है यार, जो बच्चा रोज़ा नहीं रख रहा कोई मसला नहीं है, वी एक्सेप्ट यू द वे यू आर. So I don't want this thing to crash. I hope it doesn't crash. But khair, मैं आ रहा हूँ. We've resumed the recording. अच्छा, where were we? What were we discussing? Where were we? Where were we? Where were we and what were we discussing? We were discussing what? We were discussing alcohols now. We were done with haloalkanes. We were discussing alcohols. Yeah. Chalo. Alcohols, we've already done alcohols, by the way. We've already done alcohols. Do you know why we've done alcohols already? So let me look at the syllabus एक second के लिए. कोई चीज़ तो मैंने miss out नहीं की syllabus में. Have I missed out on anything? अल्हम्दुलिल्लाह सही जा रहे हैं. ठीक है जनाब. Let's start. हम खेलेंगे. Donate it us. What's your dog name? Ribbon and Rocky. I have a lot of dogs. Lot of dogs. खैर, but yeah, nobody cares. अच्छा जी, let's start. अच्छा जी, ऐसा है क्या? Okay. Alcohols. Now, if you look at alcohols, we've already covered alcohols. Now, there's no such mechanism in your course for alcohols. No mechanism that you need to know for alcohols, right? Now, see, alkenes to alcohols, we've already done this. What do you require? You require H2O gas, you require 300 degrees Celsius, 60 atmospheres, and dilute acid, normally dilute phosphoric acid, acidified aqueous phosphoric acid. Then alcohols to haloalkanes, already covered. If you want to add chlorine atom, you could use all the reagents that we talked about. Bromine, you can use all the reagents. Haloalkanes, you could use all the reagents, right? So that's the first reaction. Then alcohols, the only reactions that are new now for alcohols is the fact that you can have aldehydes and ketones. You can have aldehydes and ketones go into alcohols, and you can also have alcohols go into aldehydes and ketones, right? Let's first discuss alcohol going into aldehyde and ketones. Remember, the mechanism for this isn't part of your course. So no mechanism. सर हमारे कॉलेज में अभी तक सिलेबस ख़त्म नहीं हुआ, 2 more lectures देन ऑर्गेनिक ख़त्म होनी. बेटा योर कॉलेज क्या कह सकते हैं हम आपके कॉलेज का. खैर, what can we do? What can we say? Okay, so let's discuss alcohols. Let's discuss 18 and 19 first, and then we will discuss all the others, right? So 18 and 19 first. We're already done. We're almost done. We're almost done. Almost done with the entire organic chemistry. Almost done, right? So if you start discussing alcohols now, you know, if I start discussing alcohols, now when we talk about the mechanisms for alcohols, mechanisms aren't part of your course, but there are certain reactions for alcohols which are part of your course. Alcohols, they can have, you first need to know, before you learn any mechanism, you first need to know the differences between tertiary alcohol, secondary alcohol, and primary alcohol. And the idea is the same. Tertiary alcohol is an alcohol which is bonded to 3 alkyl groups, or the carbon which has the OH is bonded to 3 carbon atoms directly. Then the carbon which has the OH is bonded to 2 carbon atoms directly, or 2 alkyl groups. That's the secondary alcohol. And a primary alcohol is a COH fella which is bonded to 1 alkyl group or no alkyl groups, right? All the other fellas are hydrogens, right? So this is the difference between tertiary, secondary, and primary alcohols. Now, when you talk about tertiary, secondary, and primary alcohols, how are they made? They can be made from alkenes. Again, we've studied that alkenes can make alcohols, and that's the elimination, the electrophilic addition reaction of alkenes, which is also known as hydration, in which you use H2O gas, which is steam, dilute acid as the catalyst, dilute phosphoric acid, and you use 300 degrees Celsius as pressure and 60 atmospheres, and so on and so forth. Then when you talk about alcohols, you can also make alcohols through haloalkanes. How do you make alcohols through haloalkanes? So again, NaOH, but not ethanolic. We know it's NaOH dissolved in water. It's NaOH aqueous and heat under reflux. And now you know why NaOH aqueous, because you want the hydroxide ion to act as a nucleophile. Acha, one more thing. You can either use NaOH aqueous, but sometimes your examiner also uses AgNO3 aqueous. Now, see, that's the beauty. The examiner, and in my live classes, I've taught you guys, okay, when he uses AgNO3 aqueous, there's also going to be a precipitate which will form, right? If you had a chlorine atom being bonded here, AgCl will form, which is going to be a white precipitate. You can have AgBr being forming. If the haloalkane contained the Br atom, you would have a cream precipitate, and if the haloalkane had an I atom, you would have a pale yellow precipitate, right? So you can also use ammonium nitrate aqueous and heat under reflux or heat, and you would understand that you would end up with alcohols, because if it's aqueous, the OH minus ion in silver nitrate, the OH minus ion in silver nitrate, why did I say ammonia? Sorry. The OH minus ion in silver nitrate can act as a nucleophile and end up forming alcohol. So you can also use AgNO3 aqueous, but if you're using AgNO3 aqueous, you'll also end up with precipitates, right? So if I go back to where I wrote NaOH aqueous, you could also use AgNO3 aqueous right here. AgNO3 aqueous, heat. Yeah. Will this class be uploaded onto YouTube? Yes, sure. Let's see. Maybe. Acha, next. So when we talked about alcohols, we've already studied all of this. The only two reactions that you need to know right now for alcohols are the reduction reactions and the oxidation reactions. So when you talk about the oxidation reactions, first let's talk about the oxidation reaction of alcohols. In O-level and IGCSE, you had only learned that alcohols are oxidized to carboxylic acid, but that's not true in its entirety. But you understand that alcohols, they can be oxidized to different families depending on which alcohol you have. So for example, if you have a tertiary alcohol, and if you have a secondary alcohol, and if you have a primary alcohol, there are different products which will form depending on which alcohol you have. Let's first talk about tertiary alcohol. And before I talk about tertiary alcohol, you also need to know one more thing. And that one more thing is that there's a general tip that I'm going to give you, that whenever you talk about oxidation, the carbon which has the OH must also be directly bonded to a hydrogen. Only then would oxidation happen. The oxidizing agent would give it an O, and two hydrogens are going to be removed along with this O, and it's going to form water, right? This is what you need to have for any oxidation reaction. Sir, add mind map numbers. I'm adding numbers everywhere, Zarga. I'm adding numbers everywhere. These numbers, the reason why I did not add numbers here is because we've already covered them above. I just repeated it. Right, so when you look at oxidation taking place, remember, whenever, this is a general tip that I'm going to give you, whenever you talk about oxidation taking place, the functional group that you want to, oxidize it, and the carbon that it's attached to, it must be also directly bonded to a hydrogen. Remember, so the carbon that has the OH must be directly bonded to one of the hydrogens, maybe here, maybe here, maybe here. Maybe if these two are alkyl groups, it's okay, but there must be one hydrogen at least with the carbon which is bonded to the OH. Only then can oxidation take place, right? Now, if you can look at a tertiary alcohol in which you have a carbon being bonded to three alkyl groups, let's suppose these alkyl groups are CH3s, let's suppose. So it's a carbon being bonded to three alkyl groups and an OH. Will oxidation take place? That's the question. Will oxidation take place? Will oxidation take place, everybody? It won't. Why would it not? Why would oxidation not take place? Because understand that the carbon which has the OH must be directly bonded to a hydrogen. Must be directly bonded to a hydrogen as well, but they are bonded to three alkyl groups. That's why tertiary alcohols are not oxidized. Keep that in mind. Achha, one more thing to understand as well. If you have haloalkanes, in haloalkanes, when we were performing the substitution reaction, also know that the substitution reaction will only take place if the adjacent carbon, if the carbon which has the Br atom has an adjacent carbon, sorry, elimination reaction की बात कर रहा हूँ, substitution की नहीं, elimination की. the elimination reaction that used to take place in haloalkanes, in which you used to end up with alkenes, the only reason why an elimination reaction would take place is if the carbon that has the bromine atom is directly bonded to a carbon which has a hydrogen, right? So the reason why elimination reactions would take place is if you had a carbon with the halogen atom directly bonded to a carbon which has the hydrogen. Only then would you say that the HBr is eliminated and obviously water is formed and NABr is formed, right? Only then. My question to you guys is, if you have carbons right here, and this is a CH3, let's suppose that's a CH3, let's suppose that's a CH3, let's suppose, and this is the Br atom right here, and this is hydrogen and hydrogen, would elimination reaction take place? The answer is no. Why would elimination reaction not take place? Because see, the carbon that has a Br must be directly bonded to a carbon which is directly bonded to a hydrogen. Like this, in this case, carbon that has the Br is directly bonded to a carbon which has the hydrogen. This fella is directly bonded to a carbon, but this carbon does not have any hydrogen. This carbon has alkyls. So remember, and please do not confuse it here, that the carbon which has the Br and it also has hydrogen, elimination does not take place with HBr like this. No. This is not how elimination takes place. For elimination reaction to take place, the carbon which has the Br must be bonded to another carbon which has a hydrogen. So this is just for your guys' tips. Tips, they can be tested in MCQs and normally are tested in MCQs. So this is a tip for elimination reaction. Remember this. And this is a tip for oxidation reactions, that the carbon which has the OH must have directly a hydrogen bonded to it. Done. So oxidation reaction for tertiary alcohols, they do not take place. Now the question is, what happens for primary alcohols and what happens to secondary alcohols? For primary alcohols and secondary alcohols, you can use an oxidizing agent, which you've learned in O levels and IGCSE even, which is potassium manganate, acidified aqueous potassium manganate, and heat obviously, or heat under reflux. I'm going to heat under reflux. When you do that, the secondary alcohol will go into a ketone, and a primary alcohol is going to go into carboxylic acid, right? How does it happen? The mechanism isn't part of your course, but let me show you how it happens. So if you have a secondary alcohol that looks something like this, this is CH3 right here, CH3 right here, this is a hydrogen, and this is carbonyl carbon, which is a ketone obviously. See, this fella is a ketone, no hydrogen, my man. This fella is a ketone, right? This fella is a ketone. Now how does this ketone exist? What happens is that you had a secondary alcohol which looks something like this. You have a secondary alcohol, and what happens is, see, the secondary alcohol has the OH and it also has the H. So what first happens is the oxidizing agent, what it does is it takes out both these H's, and gives it an O and forms H2O. And then the carbon oxygen double bond actually forms. That is how a secondary alcohol goes into a ketone and water is made as the byproduct. Okay, and which oxidizing agent do we use? We use acidified aqueous potassium manganate and heat under reflux. Similarly, if you have a primary alcohol, which looks something like this, one alkyl group or no alkyl group, if you have a primary alcohol, what's going to happen? What happens is you use an oxidizing agent and it gives you a carboxylic acid. How? The OH and the H. The OH and the H are removed to give you H2O, or you could think about it like this. The OH and this H is, the oxidizing agent gives it an oxygen and forms H2O. Both the hydrogens move out with this O and forms H2O, and then you're left with COH bond, right? And then what ends up happening is this CO bond forms a double bond, and this hydrogen is shifted a little to the right, and an O is also given right here. So effectively what happens is, and you don't need to know any of this, you just need to know a carboxylic acid forms from primary alcohols, right? So this is what ends up forming. Done? So from secondary alcohols, they're always going to give you ketones, and primary alcohols are going to give you carboxylic acid. And the oxidizing agent that we use is the same, acidified aqueous potassium manganate and heat under reflux. And the color change is going to be what? This is purple, acidified potassium manganate is purple, it's going to go from purple to colorless. Tertiary alcohols, they do not undergo any oxidation reactions, right? So if I summarize it for you, primary alcohols, they'll undergo oxidation reaction with potassium manganate, heat under reflux, and form carboxylic acids. And secondary alcohols, they are going to undergo an oxidation reaction with potassium manganate, heat under reflux. Remember, these are all oxidation reactions. Reaction name is oxidation. Heat under reflux, and it's going to form ketone. But there's also one more thing. You can also make aldehydes. How can you make aldehydes? Sir, you can take the primary alcohol and instead of using potassium magnate, acidified aqueous potassium magnate and heating it under reflux, what you can do is, because acidified aqueous potassium magnate is a very strong oxidizing agent. So instead of using a very strong oxidizing agent, what we do is, instead of using this fella, we use a slightly milder oxidizing agent, which is potassium dichromate. And remember, we do not heat under reflux here, because if you heat under reflux, you will still end up with carboxylic acid. What we do is we heat and distill it. We heat and distill. Because primary alcohol, it first goes into an aldehyde, and then the aldehyde further converts into carboxylic acid. Right? The aldehyde further converts into carboxylic acid. So what we do is, instead of heating it under reflux, if you heat under reflux, what that would do is the primary alcohol goes into aldehyde and then makes carboxylic acid. That's what happens when you heat under reflux. No matter which oxidizing agent you use, the primary alcohol is going to be converted into aldehyde and then converted into carboxylic acid. Even if you take potassium dichromate, acidified aqueous, and you heat under reflux, aldehyde forms and then carboxylic acid forms, right? But if you just heat it and distill it simultaneously, the aldehyde escapes and you will not end up with carboxylic acid, you will end up with an aldehyde. And there are reasons to it, because aldehydes ka jo boiling point hota hai, it's lower than alcohol boiling point, so it vaporizes, blah 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 blah, all taught in my life classes. Every explanation is given in my life classes, but I don't want to give those explanations here because it'll just take time. So for now, just understand that these are the three oxidation reactions that you need to know. Primary can directly go into carboxylic acid if you heat under reflux, but if you use a milder oxidizing agent, this is where I have ikhtilaf with teachers. Some teachers say that if you use acidified aqueous potassium magnate and you heat and distill it, this is incorrect, because acidified aqueous potassium magnate is such a strong oxidizing agent that it quickly gives you a carboxylic acid. You wouldn't even have time to distill it. That's why I say use a slightly milder oxidizing agent, which is acidified aqueous potassium dichromate. Heat and distill it and you're going to end up with aldehydes. So if you have a primary alcohol, this which looks something like this, CH3, C, OH, and these are all hydrogens, you're just going to end up with an aldehyde. Tuck, tuck, tuck. This is how the aldehyde looks, right? And end up with a 3-carbon aldehyde right here. Ethanol. So ethanol is going to give you ethanol. Done. And this is only if you heat and distill. If you heat under reflux in any circumstance, you're going to end up with carboxylic acid from primary alcohols. But if you heat and use potassium manganate and try to heat and distill it, you will still end up with carboxylic acid, because heating and distilling with potassium manganate is a very fast reaction. It's a strong oxidizing agent. K2Cl2 ke saath, the reaction is slightly slower than potassium manganate ke saath. Yes, you are right. But we couldn't care less. And so what are the numbers for it? I think the numbers are, this is number 19 if I'm not wrong, number 19, and secondary alcohol is number 20. Yes, number 19, number 20, no sorry, this is 18, thank you, this is 18. Secondary alcohol to ketone is what, 18 or 19? This is 19, this is 18 if I'm not wrong, and this is what, carboxylic acid ka 20 hai? Is it 20? You're all right. Sir, would aldehyde form if you are using K2Cr2O7 acidified only? Yes, but only if you heat and distill it. Even if you use potassium dichromate acidified and you heat under reflux, it will still form carboxylic acid. Remember this. Write it with yourself. See, if you use primary alcohol and you use the same K2Cr2O7 acidified and you heat under reflux, it will still form carboxylic acid. You have to distill it to form aldehyde. I've taught you the reasoning in the live class. Chhod the reasoning ko. Right? Just take my word for it. Next. So these were the 3 pointers for alcohols. Now let's also talk about reduction of certain compounds to make alcohols. Dekhiye, just like primary alcohol can form a carboxylic acid. How? By oxidation, using potassium manganate acidified aqueous or potassium dichromate acidified aqueous and heat under reflux, it will form carboxylic acid. The same carboxylic acid can be reduced to primary alcohol. How? By using LiAlH4. And this must be in dry ether. Why is it in dry ether? Blah, blah, blah. I've taught it in the live class. For now, just know it's in dry ether. 18 and 20 both secondary? No, these are both primary. This is secondary. Secondary makes ketone. Here, this is the only reducing agent that you can use to convert carboxylic acid into primary alcohol. Then, and which number is this? If I'm not wrong, can somebody tell me the number? It's number 22. Done? This is a reducing, मैं R लिख रहा हूँ. This is reduction reaction. I'm going to use a hydrogen. This is the symbol for reduction, hydrogen. The name of the reaction is reduction. Just like the other is oxidation, this is reduction. Next, just like you converted primary alcohol into aldehyde, how? Acidified aqueous potassium dichromate, you used an oxidizing agent and you heat and distill it. You can convert the aldehyde back into the primary alcohol. How? How? LiLH4 का name छोड़ दे. Lithium, aluminum, tetrahydride, I think, if I'm not wrong, you can search it up. I don't know. You won't be asked to name it, just write the formula for it. I think that's the name. Reduction से पहले क्या लिखा है? H. This is just hydrogen. The symbol for oxidation is O. The symbol of reduction is H. Next, aldehyde to primary alcohol. How? You can use LiAlH4 in dry ether. For now, I'm just writing the conditions. I'll explain how do you remember it forever. Why H minus 1? There's no minus. H लिखा हुआ है यार. It's just H. H just means reduction. It's a sign for reduction. क्या हो गया? Actually, you can use this. You can use sodium borohydride, and this must be aqueous. And in all cases, you heat as well, right? In all these cases, heat is involved. In all these three cases. Or you could also use hydrogen and nickel solid. The same reduction reaction that happens when alkenes go back into alkenes. It's called electrophilic addition reaction, and that's also called reduction. Alkenes to alkenes is also called reduction. Achha, this H plus, this just means acidified. This is a symbol for acidified. Acidified aqueous potassium manganate. The symbol for acidified means that there's sulfuric acid involved. You added some hydrogen ions. No, NaBH4 is not in dry ether. NaBH4 is aqueous. इतने क्वेश्चन मार्क्स चौधरी साहब आपने डाल दिए हैं, क्या हो गया? Done. So you can use either of these three. Then if you were to convert a secondary alcohol into a ketone, you can oxidize it. How? You could use any oxidizing agent. You can heat under reflux for this. You can heat under reflux with K2Cr2O7, acidified aqueous, whatever. You can even heat whatever, right? So in all cases, in secondary alcohol, just like in carboxylic acid, you could either use this fella or use acidified aqueous potassium dichromate. You would end up with carboxylic acid if you heat under reflux. But you end up with ketone. And the same ketone can go back into a secondary alcohol. How? Again, you can use any of these three. And this is called reduction. This is the reduction reaction. Now, which numbers are these? Can somebody tell me the numbers? Somebody tell me the numbers. Aldehyde to primary alcohol, क्या number है? Carboxylic acid to, this is number 22. Aldehyde to primary alcohol is what? It's number 21. अच्छा, फिर carboxylic acid to primary alcohol हो गया 22. Ketone भी 21 है, ठीक है. This is also 21. Done. अच्छा, अब I want to summarize these reducing agents with you all. अब ये सुन लें, ये आपके फ़ायदे के लिए है, लेकिन या तो ये आप रटे मारें इस पे. Although I don't recommend this, I don't recommend rote learning these conditions, but it's very easy to remember. देखिए, LiAlH4. Why do we use this in dry ether? And why is sodium borohydride NaBH4 aqueous? The reason is this is the strongest oxidizing agent out of, strongest reducing agent, what was I saying? Strongest reducing agent out of all these three. Right? In all cases we heat, but out of all these three, LiAlH4 is the strongest reducing agent. A lot of teachers teach students that hydrogen and nickel solid are the strongest reducing agent? That's absolutely BS, bullshit. No, LiAlH4 is the strongest of reducing agent, and the beauty about LiAlH4 is that LiAlH4 is so strong that if you use this in aqueous, this can even cause explosion. Because it's going to be such a quick and fast reaction, blah, 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 blah. The mechanism I can even teach, but it's not part of your course, so I'm going to skip it out, right? So the reaction is so fast that it can even cause explosion. That's why we do not use LiAlH4 in aqueous solution. We use it in dry ether. Done? To make sure that we don't cause any explosion whatsoever, right? To be safe. And NaBH4 is a slightly milder oxidizing agent, right? But you can use this as well. And hydrogen and nickel solid. Hydrogen and nickel solid is also a strong oxidizing agent. It's stronger than NaBH4 but weaker than this, right? So I'll call this semi-strong, SS. This is the strongest first, this is the second strongest, and this is the third strongest, right? Sir, while I'm impressed you teach by brain, while my PhD teacher at club uses his pre-written notes. MashaAllah, thank you, alhamdulillah, alhamdulillah. बस दुआ करें ये brain काम करता रहे. अच्छा खैर, probably they have other things to do in life, na? Other better things to do in life than to teach you all. अच्छा. Now keep in mind something. The idea is that aldehydes के साथ, with aldehydes and with ketones. But I'm going to write it like this: aldehydes, ketones, carboxylic acids, alkenes, and if I'm not wrong, in one exam it was even tested esters. In one MCQ in the 2024 exam, I don't know why the examiner tested esters, but he did, so let's talk about them. All right. Reduction. This is all reduction reaction. This is just summarizing it for you guys. देखिए, if you use a reducing agent which is LiAlH4, it will reduce aldehyde. It will reduce aldehyde to primary alcohol. It will reduce ketone to secondary alcohol. It will reduce. एक second. अस्सलाम वालेकुम जी कबीर भाई. तहजीब खो په بلو ایریا کې دی. تهذیب بس هم یو دی په اسلام. بلو ایریا کې دی زما آفیس سره. بالکل زما آفیس سره بالکل مخامخ تهذیب دی. زما چې کوم بلو ایریا کې آفیس دی کنه بالکل خوا کې تهذیب دی فرسکو سره. Okay, so it will reduce aldehydes to primary alcohols, ketones to secondary alcohols, carboxylic acid to primary alcohols. Will it reduce alkenes? Would it reduce alkenes? That's the question. Even it will first hydrolyze esters. Esters will go into carboxylic acids, and those carboxylic acids would be reduced to primary alcohols. So it can even reduce this to primary alcohols. The question is, would it reduce alkenes? Acha. Before I talk about that, I want to add hydrogen and nickel solid, the fella that we've been studying, and this is where teachers are pathetic. Hydrogen and nickel solid is going to reduce aldehydes. It's going to reduce ketones to secondary alcohol. It will reduce alkenes as well to alkenes. Alkenes are reduced to alkenes, right? Which is called electrophilic addition reaction. Esters के साथ इसका कोई लेना देना नहीं है. But if you talk about carboxylic acids, would hydrogen and nickel solid reduce carboxylic acid? This is the most common confusion among students and with teachers. It's the difference between these two. Now let me tell you. Some teachers, let me tell you what they say. Some teachers say that hydrogen and nickel solid is the strongest of reducing agents. It's the strongest of reducing agents. That's why LiAlH4 is not able to reduce alkenes, whereas hydrogen and nickel solid can reduce alkenes. This is what some teachers claim. Okay. If those teachers are claiming this, that LiAlH4 is not able to reduce alkenes, but hydrogen and nickel solid, because it's stronger than LiAlH4, it can reduce alkenes to alkenes, right? This is what these teachers say. It can reduce alkenes to alkenes, and you've seen it. The problem is that carboxylic acid is not reduced by hydrogen and nickel solid. फिर क्या? Hydrogen and nickel solid cannot reduce carboxylic acid to primary alcohol, whereas LiAlH4 can. Now this is a problem. And to those teachers, I'll say, get your knowledge straight. LiAlH4 is the strongest of oxidizing agent. Strongest of reducing agent. It can reduce every single family except for alkenes. Do you know why? Do you know why? The reason is that it works in a different manner. It does not reduce alkenes is because LiAlH4 and even sodium borohydride, they both work on the idea that they can only reduce polar pi bonds. They can only reduce polar pi bonds. Now, if you look at these aldehydes and ketones, they all have polar pi bonds. This is an aldehyde. See, this is a polar pi bond. And this is why LiAlH4 can work. LiAlH4 and even sodium borohydride. Even sodium borohydride can work. See, if I add sodium borohydride, the mechanism on which these two fellas work is aldehydes have a polar pi bond. How does it have a polar pi bond? Right here. This is a partial positive carbon. This is a partial negative oxygen. And this pi bond is therefore polar. So they work on the idea of polar pi bond. That's why it can reduce aldehyde, it can reduce ketones. But when it comes to alkenes, both these fellas cannot reduce alkenes. Why? Because alkenes there is a pi bond present, but it's not polar. That's the reason why LiAlH4 is not able to reduce alkenes, even though it's strongest reducing agent. It's the strongest reducing agent. Therefore, LiAlH4 can reduce anything and everything except for alkene, because alkenes do not have a polar pi bond. It has a pi bond, but the CC bond is non-polar. That is the reason why alkenes are not reduced by LiAlH4. If hydrogen and nickel solid were stronger reducing agent than LiAlH4, then they must have been able to reduce carboxylic acid, but they can't. And what that means is, if they can't reduce carboxylic, that means that hydrogen and nickel solid is not as strong as LiAlH4. It's the mechanism difference. Hydrogen and nickel solid, they can use the catalyst mechanism to reduce alkenes into alkanes. But remember, they can't reduce carboxylic acids because they aren't that strong. Similarly, NaBH4, sodium borohydride in aqueous state, it is a milder oxidizing agent. Hence, it cannot reduce carboxylic acid. Neither can it reduce esters, because esters are first hydrolyzed to carboxylic acid, and then carboxylic acids are reduced to primary alcohol. And the only reducing agent which does this is LiAlH4. No other. So this is the complete summary of all your reducing agents. Remember this. These are the 3 reducing agents, and if you know this table, you'll be good to go. Sir, can't we leave everything and just remember LiAlH4 as the only reducing agent for all? No. The reason is that when the examiner tests your organic synthesis knowledge and when he gives you MCQs, he will not just use LiAlH4, will he? So remember this. Done, guys. So when you're dealing with esters, the only fella which reduces esters is what? LiAlH4. Because it first goes into carboxylic acid and then goes into primary alcohol. Let me also take a picture for this. यार मैंने बड़ी अच्छी चीज बनाई है. Took a picture for this. Achha, if you take an aldehyde, by the way, if you take an aldehyde and you oxidize an aldehyde, further oxidize an aldehyde, what would it form? Aldehydes would form carboxylic acids. Done. एल्डिहाइड को अगर आप ऑक्सीडाइज करते हैं कार्बोक्सिलिक एसिड ही बनता है ना. दिस जस्ट जनरल, इसलिए तो आप हीट एंड डिस्टिल करते हैं. अच्छा, डन गाइस. दिस टेबल इज अ गुड टेबल दैट आई केम अप विद. अच्छा, नेक्स्ट, हाउ टू नो. So alcohols is finished, by the way. Alcohols is gone. If you look at the alcohols bit, it's gone. If you go back into your mind map, alcohols is completely covered now. This is done. See, aldehydes to alcohols, it's reduction. This is reduction. This is reduction. And I've added 21, 21.1, 22. Alcohols to carboxylic acid, this is oxidation. We've already done it. You can use oxidizing agents, heat under reflux, right? And alcohols to aldehydes and ketones, again oxidation, but this must be a secondary alcohol and this must be a primary alcohol and this is also a primary alcohol. Done? So you're done with alcohols. Alcohols is over. Done, guys? Alcohols is done. Now we have to deal with aldehydes and ketones. Bas khatam. Almost over. I'm going to give you guys a 5 minutes break और फिर इसको मुकाते हैं. We are almost done. ये ऐप क्रैश ना हो जाए बस. This map looks like biryani to me. सर आपका इस्लामाबाद में अपना घर है या फ्लैट? नहीं, मेरा अपना घर है. एनालिटिकल का लेक्चर अपलोडेड है, 40 मिनट में मैंने पढ़ाई है एनालिटिकल. यू कैन वॉच माई यूट्यूब वीडियो फॉर इट. सर अनब्लॉक मी ऑन इंस्टा. आई हैव नॉट ब्लॉक्ड यू जरगा खोजा. कैन वी गेट दीज नोट्स? दीज नोट्स विल बी अपलोडेड ऑन द पोर्टल. लेकिन मतलब ये ऐसे मैं शेयर नहीं कर सकता एज इन लाइक, चलो मैं शेयर कर दूंगा ग्रुप में, मैं शेयर कर सकता हूँ. लाइक यूट्यूब पे तो मैं शेयर नहीं कर सकता ना. आई शेयर इट इन द ग्रुप्स. इफ यू वांट आई शेयर दिस नोट्स इन द ग्रुप्स. हैप्पी? आहिस्ता आहिस्ता एनर्जी जा रही है यार. हैं, द स्क्रीन इज पॉज्ड. व्हाट द हेल? सर आप ऑर्गेनिक सिंथेसिस करवा गए हैं? नहीं, अभी बस ख़त्म. ये ऑर्गेनिक सिंथेसिस ही करा रहा हूँ और क्या करा रहा हूँ. मुर्तज़ा ऑर्गेनिक सिंथेसिस ही तो है. ओके, मूविंग फॉरवर्ड. नाउ वी टॉक अबाउट aldehydes and ketones. Let's start talking about aldehydes and ketones. The iPad is now slowly and gradually starting to become stuck. अब आहिस्ता आहिस्ता iPad is getting stuck. It's getting very laggy. I don't want this to effectively break. इसको ना मैं ज़रा sorry guys for wasting your time. Yeah, what the hell did I do? There's something wrong with the app now. The app has started to glitch now, guys. Sir, why can't aldehydes be oxidized to ketone? No. Why would aldehyde be? Ketones are formed from secondary alcohols and ketones can't be. Acha, one more thing. Thank you for asking this question. One more thing, guys. When ketones form, can ketones be further oxidized? Remember, I gave you guys an idea. And what was the idea? That for oxidation, the fella which has the functional group must be bonded directly to a hydrogen for oxidation. Would ketones be oxidized? This carbon has the double bonded to, this is the carbonyl carbon. Will it be oxidized? See, aldehydes can be oxidized to carboxylic acids because see, you have C double bonded to OH and oxidizing agent gives it one more O right here, and that's how carboxylic acids form. But can ketone be further oxidized? Keep this in mind, ketones cannot be further oxidized because see, there is no hydrogen directly bonded to the carbon which has the functional group. So keep this in mind as well. Let me also write it. Ketones tip. Ketones can't be oxidized further. होता वैसे है in reality, but for you guys नहीं होता. It's just highly unlikely. अच्छा, now we are going to talk about carbonyl compounds. Now carbonyl compounds are either ketones or carboxylic acids. Carbonyl compounds are those compounds, ketones or aldehydes. Carbonyl compounds are those compounds which have the carbon double bonded to O. Now you might even think, sir, the carbonyl carbon double bonded to O is also present in carboxylic acids and its derivatives. Please understand that we do not club it under the umbrella of carbonyl compounds. The term carbonyl compound is specifically used for aldehydes and ketones, not for carboxylic acids. Why? I will teach that in A2 chemistry, if there is A2 chemistry that I have to teach. So that's the idea that you need to keep in mind, Adreno. Done? So these are the only two carbonyl compounds. Now, how do you know if a carbonyl compound is present? Well, we use a test for it. The test is called 2,4-DNPH test. It's called 2,4-dinitrophenylhydrazine. Nobody cares. But when you use 2,4-DNPH, if ketone and aldehydes are present, effectively if C double bonded to O is present, you are going to get a test, which is you are going to get an orange precipitate or a yellow precipitate. Sometimes examiners also write red, but orange or a yellow precipitate. Why, how, whatever, I've taught all of that in the live class. Couldn't care less. But if you were to test for the carbonyl carbon, remember, it would only give you a result. A carbonyl carbon would only give you a result with 2,4-DNPH. And then that would mean you have a ketone or an aldehyde. My question to you guys was, will carboxylic acid give you a result with 2,4-DNPH? It also has the carbonyl carbon, doesn't it? But please understand, it will not give me any result, because I told you carbonyl compounds are only ketones and aldehydes. So no test of carboxylic acid with 2,4-DNPH. These are common confusions. Teachers ये आपको नहीं पढ़ाते. Teachers will leave it and then in MCQs आप फिर रोएंगे. So these are just some things that you need to know. Done. Then once you've identified KR, whether it's a ketone or whether it's an aldehyde, the further thing is KR with 2,4-DNPH, I figured out that there's a carbonyl carbon present, which means that it's either a ketone or it's an aldehyde. Now, how do you further test it? It's a ketone or an aldehyde. How do you distinguish between the two further? You know that aldehydes can be further oxidized, whereas ketones cannot be further oxidized. So what we do is we use mild oxidizing agents. And which two mild oxidizing agents do we use? We either use Toland's reagent or Felling's or Benedict's. Felling or Benedict, you can search the spelling. Felling or Benedict's solution. And in both these two cases, would they oxidize ketones? Can ketones be oxidized further? These are oxidation reactions, right? Can ketones be further oxidized? हाँ जी बताएं. No, so this will not give you a test with ketone, this will not give you a test with ketone, and it will give you a test with aldehyde and a test with aldehyde, right? And what would be the observations? If you use Toland's reagent is effectively silver nitrate aqueous, and it is silver nitrate aqueous, and it's ammoniacal. Or you could, instead of writing ammoniacal, because my spelling is incorrect, you can write dissolved in ammonia. Now, why must this be dissolved in ammonia? The reason why this is dissolved in ammonia is because Toland's reagent only works if you have complex ions. And what are complex ions? You learn that in A2 chemistry. Done? So understand that Toland's reagent is effectively silver nitrate aqueous dissolved in ammonia to make complex ions, because it's only complex ions which will give you a test. And what are complex ions? You learn that in A2 chemistry. And what is the observation? The observation is you end up with a silver mirror. That's the observation. Silver mirror is effectively just like, it's a colorless solution and then silver starts to deposit. And the reason why this happens is because it's an oxidizing agent. The silver ions are reduced. They reduce themselves. The silver ions reduce themselves to oxidize the aldehyde. See, that's why we call them oxidizing agent, because what is an oxidizing agent? A chemical which reduces itself. It went from silver ion, there's a decrease in oxidation number. It went from a silver ion to silver. So a chemical which reduces itself to oxidize others. Done? Easy peasy lemon squeezy. That's it. So you're going to observe silver. Now, when in paper 3 you guys are performing this experiment, please understand that normally you don't end up with a silver mirror. Normally you guys end up with a black, something that looks black. Normally it's like a blackish mirror in labs. Yeah, and the reason is because the test tubes are not clean. your lab assistants have not cleaned the test tube. It's like grayish, blackish solid, grayish solid, you know, blackish solid gray solid, because it's not clean. But in the exam, even in P3, just write even if you end up with a black solid, you'll say it ends up with a silver mirror. And similarly here, Felling solution and Benedict solution are effectively copper 2 plus ions. They have copper 2 plus ions, right? And that's actually blue. So copper 2 plus ions, Felling solution and Benedict solution is a blue solution because of copper 2 plus ions. And because they are oxidizing agents, these copper 2 plus ions, they oxidize the aldehyde into carboxylic acid, but themselves they get reduced, copper 1 plus. And this copper 1 plus actually reacts with the oxide ion and gives you a red precipitate, which is Cu2O. So effectively you go from a blue solution into a red precipitate. This is the observation. And that's all. So how do you differentiate whether you have a carbonyl compound present or no? You use ketones and aldehydes and react it with 2,4-DNPH. If it gives you a yellow or orange precipitate, it will give you guys a yellow and orange precipitate. That means that the carbonyl compound, the C double bonded to O, is present, and it's either a ketone or an aldehyde. And to further investigate whether it's ketone or aldehyde, you either use Toland's reagent, which is silver nitrate aqueous dissolved in ammonia, or you use Felling's or Benedict solution. But you need to know the observations as well. Sir, I swear you do this so effortlessly. Why can't we be like you? I don't know, man. Sir, is 2,4-DNPH in the whole syllabus for carbonyl? Yes. Remember, it will not give you a test with carboxylic acids. सर बेनेडिक्ट सोल्यूशन तो बायो में होता है, हाँ होता है फॉर रिड्यूसिंग शुगर से। ये इधर भी इधर ऑक्सीडेशन, वो बेनेडिक्ट सोल्यूशन है, ये भी बेनेडिक्ट सोल्यूशन है। बोथ वर्क ऑन द आइडिया ऑफ कॉपर 2 प्लस आयंस। यू आर राइट, होता है। These are mild oxidizing agents. You can also call this ammoniacal silver nitrate. Sir, why can't the physics teachers, क्या? Why can't physics teachers not be like in? कौन से physics teachers? No. Why would we even use 2,4-DNPH for carboxyl? No, I'm just saying a lot of students confuse this now. A lot of students think that 2,4-DNPH is going to give you guys a test with carboxylic acid, and the answer to that is no, it won't. That's all I said. Done. आसान। कोई मुश्किल कोई अच्छा, finally last, बिल्कुल last, and then we're going to move on to the past paper questions. बिल्कुल final is the aldehydes and ketones reaction. The only reaction that is part of your course for aldehydes and ketones. I've added all the numbers of the mind maps यार. I've added all the numbers. Just give me a moment. ये भी add कर देता हूँ ना. Relax. ये तो सिर्फ tests कराएं. ये तो उसमें है ही नहीं. These aren't part of the mind map. ये tests तो mind map में लिखी नहीं हुई. The last thing to note is that aldehydes and ketones have only one reaction which is part of your course, which is called the nucleophilic addition reaction. And through this nucleophilic addition reaction, you will end up with, please remind me at the end, I also have to teach you iodoform. At the end, remind me this, right? ये बस एक रह जाएगा, वो मैं पढ़ाता हूँ आपको एंड में। तो बस बिल्कुल ऑर्गेनिक केमिस्ट्री का हर एक रिएक्शन ख़त्म हो जाएगा। ये remind me this at the end, please. And remind me the test for alkenes and alkenes difference, and the test for alcohols. Please remind me these three things. Somebody please towards the end remind me this. I'm just left with one this, and then carboxylic acids का बस एक करना है, esterification. Man, I'm so tired. Cooked. Okay. And this nucleophilic addition reaction will give you hydroxynitriles. Sir, what exactly do you mean by this? क्या चल रहा है, क्या नहीं चल रहा? Let me talk about it right now. Basically, if you have an aldehyde, I just use aldehyde. You can also have ketones. Like let's suppose this is an aldehyde ethanol. Now what happens is the reagents for the nucleophilic addition reaction is, and which number is this if I'm not wrong? It's number 24 and number 25, right? So if you have, and this is called nucleophilic addition reaction. Now what we do is we use reagents, which is NaCN or KCN, and HCN, and then it is aqueous, and then we heat. NaCN, HCN aqueous, or KCN aqueous and HCN aqueous, and then heat, or heat under reflux. And that's going to give you guys what? That's going to give me hydroxynitriles. They're going to convert these carbonyl compounds into hydroxynitriles. Now what exactly is a hydroxynitrile and how does it do that? It's pretty simple. Basically, what happens is, please understand this as well. Why do we use NaCN and why do we use KCN simultaneously? Again, you don't need to know why you do this, but let me just quickly tell you. Basically, what happens is NaCN is a catalyst. Why is it a catalyst? Because when you have NaCN, it is going to give you the sodium ion and the cyanide ion, and it is this cyanide ion which will be used as a nucleophile for the nucleophilic addition reaction. Sir, but then why do we use HCN? I'll tell you why you use HCN. HCN is a very weak acid. It gives you the hydrogen ion and the cyanide ion, but this is not the cyanide ion which is used as a nucleophile. No, because this is in a very, very, very low amount. Basically, what we do is to use HCN is not to end up with the cyanide ions, it's effectively to use HCN in totality. We need this fella and we need this fella for the reaction, right? So effectively, sodium cyanide is a catalyst. Why is it a catalyst? You learn that in a moment, because it does not get used up. The cyanide ion starts the reaction and forms at the end of the reaction once again. But the HCN is not responsible for giving you cyanide ions. Remember this, the HCN is used in totality to give you the hydrogen ion. I'll show you how it gives you hydrogen. Because see, if you guys thought that the HCN was, the cyanide ion came from HCN, you're absolutely incorrect, because this fella is a weak acid. It only dissociates 1%. You're only going to have 1% cyanide ions. That's the reason why we use sodium cyanide along with HCN, because sodium cyanide is going to give me the cyanide ions for the reaction, and HCN is going to give me the hydrogen ion. How? Let me show it to you right now. So if this is an aldehyde with me, the cyanide ion comes from what? The cyanide ion comes from sodium cyanide or potassium cyanide. It attacks this partial positive carbon right here, right? And this is partial negative oxygen, right? Partial negative oxygen right here, because there's electronegativity difference. The moment this cyanide attacks this fella, the CO bond breaks, because we know carbon cannot make 5 bonds, so one of the bond must break. Which bond breaks? The pi. These are all sigma bonds. So we know that between sigma bonds and pi bond is weaker than the sigma bond, so the pi bond breaks simultaneously. This fella makes a bond here and this pi bond breaks simultaneously. Both the electrons go to O. So what happens is you end up with this fella having one O. And why is there a minus here? Because the two of the electrons, both electrons in the pi bond, went to this O right here. So you end up with this. This is CH3 as is. This is hydrogen. It's a tetrahedral shape, right? And this is the cyanide ion which formed. This is the CN which formed. And then you also have HCN present in the solution. So if HCN is present, what happens is this is partial positive and this becomes partial negative, right? Because the cyanide fella is more electronegative than hydrogen. So this is partial positive, partial negative, and this O has a lone pair. Let me add the lone pair here, right? The lone pair that came from the pi bond. It has other lone pair as well, but I'm just talking about the lone pair that came from the pi bond. And this is the lone pair right here. I don't know, the video is getting stuck now. And this lone pair attacks this hydrogen right here from the HCN, hydrogen cyanide, and then this HCN, it breaks, and the HCN bond breaks heterolytically, and you end up with C bonded to OH, bonded to CH3, bonded to a cyanide ion, and bonded, or cyanide, not ion, but bonded to cyanide, and hence this is again tetrahedral, and you end up with the cyanide ion at the end. So you realize that, hey, cyanide ion was effectively a catalyst. It started the reaction, but then at the end of the reaction, it was formed again. This is one way to write the mechanism. The other way is to show the intermediate like so. So the other way is to show, normally the examiner follows this. You can use either or, it's up to you. You can also say that the HCN, because it dissociates to at least 1%, it still gives you hydrogen ions, right? The HCN still gives you hydrogen ions. So you can also just write hydrogen ion like so. It's up to you. You can show it like this as well. Now, in the 2024 exam and the 2023 exam, they used to show it like this. Before, they used to show it even like this. It's up to you. Both are correct. Even this is correct and this is correct. This hydrogen ion came from the HCN, or you could use it in the form of a molecule. Both are equally correct. It's up to you how you want to show it, right? So this is effectively the nucleophilic addition reaction. Why? Because a single product is made. That's why it's addition. See, nothing has been substituted. All the atoms are present and everything is the same. And why is this called hydroxynitrile? It's called nitrile because see, it has a CN. Why hydroxy? Because you have 1, 2, 3 carbons in the longer chain. This is propane nitrile. Propane nitrile. There are 3 carbons. And on the second carbon, see, 1, 2, 3. On the second carbon, you have a hydroxy. Remember, when the OH becomes a substituent, it's not called alcohol anymore. It's called hydroxy. So it's 2-hydroxy propanitrile. And normally, always you're going to end up with 2-hydroxy. You're going to end up with the hydroxy on the second carbon. Except if you have methanol, then obviously you're going to end up with. If you have methanol, then you are going to end up with hydroxy ethane nitrile. Then hydroxyethane nitride. Other than this, you're only going to end up with the hydroxy being bonded to the second carbon in the chain, always. Done. Heat under reflux is better. Yes, you say heat under reflux, because obviously this concept of heat under reflux is very easy. The moment you see reflux, the moment you see volatile products and reactants, you heat under reflux to prevent them from escaping. Sir, I am impressed with the, please teach me your way of memorizing this. I don't memorize anything, Muhammad Hamid. This is all conceptual. I have not memorized anything. Because see, I make, my brain works like this, if it's NaCN and KCN, there's a reason. CN is basically, this is a catalyst. It'll give you the cyanide ion. Then why do you use, I ask myself, why am I using HCN? What's the purpose of using HCN? And so that's how it'll help you out in mechanisms as well. Watch my introduction to organs. So show your biceps. I don't have any biceps. I have noodle arms. Noodle arms, spaghetti arms. Done. So we are also done with aldehydes. And then again, one more thing to understand is that this propane nitrile can further be hydrolyzed. So you can again use dilute acid here. And what will happen if you use dilute acid here? What will happen? This CN would go into COOH, right? So you're gonna have C bonded to OH. This is a CH3, is going nowhere. This is hydrogen, and this fella would go into COOH, which is and you obviously use dilute acid and heat, which is obviously carboxylic acid. So you can also convert hydroxynitriles into carboxylic acid, and this I think is number 26. So this is number 26. And then number 27 kya hai? Number 27 is esterification. Esterification is a piece of cake. Esterification will happen when you have alcohol reacting with carboxylic acid plus carboxylic acid. And we use normally, what do we use? We use conc acid. We use concentrated acid, either concentrated sulfuric acid or concentrated phosphoric acid, and we heat and we end up with ester, which are sweet smelling compounds. And again, the alcohol loses the hydrogen and the carboxylic acid loses the OH, and this ends up making water. That's why it's also called a condensation reaction, by the way. How does it happen? Let's suppose you have this alcohol, which is ethane 1-ol, and you have this carboxylic acid, which is, let's suppose, propanoic acid. The alcohol loses the hydrogen and the carboxylic acid loses the OH. It gives you H2O, and they just join. So it's CH3 bonded to CH2. This is O, this is COO, this is CH2, CH3. This part came from the carbon double bonded to oxygen and all the other carbons. This is coming from carboxylic acid, and this part is coming from alcohol, which is meth. This will become, it says hold on, optimizing storage. This will become ethyl, and this will become methylpropanoate. So the name is ethyl propanoate. The carboxylic acid's name changes into OAT. OA की जगह OAT आ जाता है, and alcohol की जगह ethyl आ जाता है, YL. 26 reaction name is called condensation. Oh, this is called hydrolysis. क्या हो गया? 26 is hydrolysis. It says hold on, optimizing storage. Hydrolysis. Done. That's all. The last reaction is iodoform reaction. The last reaction is iodoform. I'm quickly doing it because obviously the app is getting stuck now, and it's gonna, I don't want it to crash because everything will just get destroyed, right? If it crashes, everything is just destroyed then. तो प्लीज़ लेट्स जस्ट क्विकली डू इट. आयोडोफॉर्म रिएक्शन क्या है, बस बिल्कुल सिंपल करें. इट्स सोडियम यू यूज सोडियम हाइड्रोक्साइड एक्वस एंड you use iodine and you warm, and this will give you a test only if you have methyl ketones. Let's just write it here. Only if you have methyl ketones or if you have secondary alcohols. If it's a primary alcohol, you guys can use your logics later on. If it's a primary alcohol, it can only be ethanol. And if it's a an aldehyde, it can only be ethanol. Why? Because understand that this reaction, the iodoform reaction, also known as triiodomethane, it will only give you a test for CH3 bonded to CO group of atoms. This is what it gives you a test of, and this actually is a yellow precipitate which forms. So the only way the iodoform reaction will take place is if you have a carbonyl carbon directly bonded to a CH3. This bond ends up breaking and you end up with this CH3 converts into CHI3, which is called triiodomethane, and this entire fella becomes something like this. This becomes O minus Na plus. This becomes a salt. Right, so this goes into this, and then this salt can further be acidified and you can end up with acid as well. It's up to you. And this can only happen if you have either methyl ketones, so this can be R, or if it's an aldehyde, it can only happen if you have a ethanol, because if it's not ethanol, then CH3CO cannot exist. This reaction can only happen if you have CH3 directly bonded to CO. And if it is a primary alcohol, it can only be ethanol, because primary alcohol will go into ethanol will go into ethanol, which will do something like this. Where does the hydrogen go? Where does everything go? Ethanones, methyl ketones या ethanol. It's called methyl ketones, not ethanones. Methyl ketones के साथ होगा, कोई भी methyl ketone. Because see, if you have a methyl fella with, it is ethanone की अगर आती, there's no such thing as ethanone. It's the smallest ketone is propanone. This, I just did not show this bond. See, no matter how many R's you have here, as long as you have methyl ketone, which is CH3 bonded to a carbon, double bonded to O, the iodoform reaction will take place, and you're going to end up with a yellow precipitate, which is because of this fella. This fella is a yellow precipitate. So remember, this reaction will only happen with these four. Other than these four, reaction will not happen. Will this give you guys a reaction with carboxylic acid? The answer is no. No reaction with carboxylic acid, no matter what. Whatever it is, no 2,4-D and PHP carboxylic acid के साथ कोई reaction नहीं देता. Neither will this give you a reaction. It will only give you methyl ketone के साथ, secondary alcohols if any, primary, if it gives you a test with primary alcohol, it's only ethanol, aldehyde के साथ, it's only ethanol. Because these are the only two cases in which, in ethanol and ethanol, these are the only two cases in which this type of structure can exist. Other than this, in no aldehyde or in no primary alcohol can this type of structure exist. That's all. Done. We are done with entire organic chemistry. हाँ, एक test है alkane alkene में difference. I wanted to go into more detail for that test, but since that test is useless for me, I'll just write it. If you were to differentiate between alkane and alkene, how do you differentiate between alkane and alkene? You can either use bromine liquid or bromine aqueous. If you use bromine aqueous, you're going to go from, in alkenes, you're going to go from a test which is, bromine aqueous is orange by the way. So you're going to go from orange to colorless. It'll decolorize bromine aqueous, and in alkene, it'll remain the same. It'll remain orange. The color stays the same. But if you're using bromine liquid, then you'll go from brown to colorless, because bromine liquid is brown. So you either go from brown to colorless, or if it's with alkane, this is alkene, right? If it's alkane, it will remain brown. That's the test. Done. Khatam, finished. Love you. Will pray for you after namaz. Thank you so much. Thank you, Ji. Thank you. Now I'm going to start organic synthesis ke sawal, because only after all of this will you be able to do organic synthesis. I've effectively revised your entire organic chemistry with you. My gala is done for, like done tara कहते हैं क्या नो से बारा, right? तो ये है. हाँ सर, अल्कोहल का टेस्ट क्या है? अल्कोहल के लिए यू कैन यूज सोडियम मेटल. लेट्स रिमेंबर वन मोर थिंग. सोडियम मेटल Last thing, sodium metal will give you hydrogen with both. It'll react with alcohols as well, give you hydrogen, and sodium metal will react with carboxylic acids as well. Right? Metal plus acid displacement reaction. But with alcohol, the reason why sodium metal reacts with alcohol is because alcohols are slightly acidic. They're not an acid, they're slightly acidic. Why are they acidic? Slightly dafa kare goli mare. I've taught it in life class. Similarly, sodium carbonate. This sodium carbonate is a weak base. It'll react with the acid, but it will not react with the OH of the alcohol. It will not react with the OH of the alcohol because alcohol is not an acid. This is a weak base. So alcohols will not react with these weak bases. Alcohol can only react with sodium metal to give you hydrogen, and sodium carbonate can react with only this acid, not with alcohol. What is the test for alcohol? You can add PCl5s, and if you see steamy fumes, that would mean that the OH of the alcohol is present, absolutely. And PCl5 can also, give you steamy fumes with carboxylic acid, because PCl5, we know it can react with the OH of alcohol as well as the OH of carboxylic acid. If you want to further differentiate whether an alcohol or carboxylic acid is present, use sodium carbonate, because sodium carbonate will not react with the alcohol, rather it will react with the carboxylic acid, since acid-base reaction will take place. Alcohol is not an acid, तो इसके साथ कोई reaction नहीं होता इसका. Tertiary alcohol oxidize नहीं होते. खुश होंगे? None. How do you differentiate between primary alcohol and secondary alcohol? देखिए, it's very easy. Primary alcohol, secondary alcohol में कैसे करें? Add potassium dichromate to it and heat and distill it. K2Cr2O7. Add acidified aqueous potassium dichromate and heat and distill. And if you heat and distill, if it's a primary alcohol, it'll give you an aldehyde, and if it's a secondary alcohol, it'll give you a ketone. And then you can further use mild oxidizing agents, and if your mild oxidizing agent gives you a test like silver mirror forms or red precipitate forms, that means that the alcohol that you guys had was a primary alcohol. And if it does not give you any test, then that means if the solution remains colorless or in blue in case of Fehling solution or Benedict solution, then the alcohol that you had was a secondary alcohol. I have not PCl3 तो नहीं है, PCl5 है. It's yesterday. How do you go from an alcohol into a haloalkane? PCl5 इस्तेमाल कर सकते हैं, PCl3 इस्तेमाल कर सकते हैं, either or, HCl के अलावा. So it'll give you steamy fumes. Can you go back to iodoform for 1 second? Absolutely. मैंने effectively सारी organic chemistry आपको करा दी. And see, these notes are now getting pathetic because everything is now getting blurry. This app is gonna crash, so I'll stop recording here, but it's done. बढ़ गया ऐप तो जी बढ़ गया. I think ऐप बढ़ गया. अच्छा हाँ, नहीं बढ़ा पूरा. But those who want to read the notes, you won't be able to read it. देखिए ना क्या गंद मच गया. Can you guys see this? I think, is it possible? It's now all blurry. सर इतना डिटेल कॉलेज में टीचर ने नहीं पढ़ाया, जितना 1 मंथ में भी नहीं पढ़ाया, जितना आपने 5 घंटों में पढ़ाया. बस ये यार फ़र्क होता है बंदे का, क्या कर सकते. सर गो लिंक. सर सेव द नोट्स. हाँ यार, इसको मैं अभी से सेव कर देता हूँ. आयोडोफॉर्म मैंने बड़ी तेज़ी से इसलिए पढ़ा है, वो ख़त्म हो रहा है ना. बस यही आपको पता होना चाहिए आयोडोफॉर्म के लिए. और क्या कहूँ, इसको मैं जल्दी वो कर देता हूँ, ये ऐप क्रैश ना हो जाए यार. इट्स एक्सप्लेन एवरीथिंग. ये तो स्टक हो गया जी, बढ़ गया. सर नोटेबिलिटी इस्तेमाल करें यार. नोटेबिलिटी और गुड नोट्स में इस्तेमाल करता हूँ, लेकिन उसमें इनबिल्ट रिकॉर्डिंग मैं नहीं कर सकता ना यार. अब ये स्टक हो गया, क्या करूँ. ओह, हो गया कुछ ना कुछ. हो रहा है कुछ तो कर लिया. चलो जी. ये जो रायमा रो रही थी क्लास में, सर आप पूरा माइंड मैप करा दें, पूरा 10 दफ़ा तो माइंड मैप कराया, लेकिन रायमा आप क्लास में नहीं है. लेकिन रायमा, अगर आप ये लेक्चर देख रही हैं तो जी आप खुश हो गई हैं, पूरा करा दिया है. सर आईपैड तो गर्म नहीं हुआ नहीं, ये तो लेटेस्ट आईपैड है, क्यों गर्म होगा यार. अच्छा, अब आप लोगों का कोई सवाल है तो आप मुझसे पूछ सकते हैं. अब हम ऑर्गेनिक सिंथेसिस करने जा रहे हैं. सर ग्रुप में भेजें. ग्रुप में भेज देता हूँ, ये क्लास ख़त्म हो जाए मैं ग्रुप में भी भेज देता हूँ, कोई इशू नहीं है. क्लास में भेज देता हूँ, कोई इशू कोई भी इशू नहीं है. अच्छा, मेरा एक वैसे सवाल है आप लोगों से. A2 का सेशन अगर मैं कभी A2 पढ़ाऊंगा ना तो कोई अगस्त सितंबर, और A2 का कोर्स बहुत छोटा है. A2 इज जस्ट ऑर्गेनिक केमिस्ट्री. A2 में कोई कोर्स है ही नहीं. AS का कोर्स इज द लेंथीएस्ट आउट ऑफ ऑल कैम्ब्रिज सिलेबाइज. AS केमिस्ट्री इज द लेंथीएस्ट कोर्स आउट ऑफ एवरी सिंगल सब्जेक्ट. इसके अलावा A2 का जो कोर्स है ना, अगर AS मैंने 134 आवर प्लस में पढ़ाया है ऑलमोस्ट, और प्रैक्टिस सब कुछ मिला के देयर आर अबाउट 200 आवर्स ऑफ कंटेंट. AS इज अबाउट 60 आवर्स. A2 is about 60 hours. That's all. Sir, does secondary react as SN2 or SN1? Maz, I said this a billion times. The examiner will tell you whether it's SN2 or SN1. Secondary haloalkanes का वो आपको बताएगा, because it depends on certain groups bonded to it. So it will tell you whether it's SN1 or SN2. Examiner will always tell you. ठीक है ना? So you will not be expected to know this because it depends. Yeah. तेरी अब सवाल करें. A2 अगर मैं पढ़ाऊंगा यार, कोई देर में पढ़ाऊंगा, कोई सितंबर में जाके पढ़ाऊंगा अगर तो पढ़ाऊंगा. ये मुश्किल है यार, मेरा काम इतना ज़्यादा हो गया फर्म में कि आई डोंट नो. हाँ, मैं आप लोगों से कोई सवाल पूछ रहा था, भूल गया. हाँ, I've covered your entire organic synthesis and organic chemistry by the way, except for isomerism, क्योंकि वो 15-20 लेक्चर्स की बात है. आइसोमेरिज्म टीचर्स तो आपको रटवा देते हैं. मैंने 15, 16, 17 लेक्चर्स आइसोमेरिज्म पे लगवाए हैं, तो डोंट एक्सपेक्ट मी टू टीच आइसोमेरिज्म हियर. खैर, ऑर्गेनिक केमिस्ट्री तो हो गई सारी. मेरा सवाल ये था कि अगर फॉर एग्जांपल एक ऑर्गेनिक मॉलिक्यूल है, if there is an organic molecule and it has ester linkage, it has ester linkage, it has ketone, it has aldehyde, and then when I reduced it, it had ester linkage, it had secondary alcohol, and it had primary alcohol. Acha, which reducing agent did I use? There was ester, ketone, aldehyde in a particular organic molecule. I reduced it and I had ester, the same ester. I had secondary alcohol and primary alcohol. Which reducing agent did I use? And this is where you all are wrong. अच्छा, अब सुनिएगा. Shahir is saying hydrogen and nickel heat. That's correct. जो LiAlH4 कह रहे हैं, you're all incorrect. Do you know why? Because LiAlH4 will also reduce ester into primary alcohol. I said you had ester, primary alcohol, you had ester, aldehyde, ketone. Aldehyde, ketone तो LiAlH4 कर सकते हैं, लेकिन वो तो ester को भी primary बना देगा ना. So you can either use hydrogen and nickel solid and heat, or you could use NaBH4 aqueous. Next, I have another question. What if you have in an organic molecule, you have ester, you have aldehyde, you have ketone, and you have alkene, and then I reduced it and I still had ester, I had secondary alcohol, I had primary alcohol, and I had alkene. Like the double bond broke. Which reducing agent did I use? Always think in this broader perspective. NaBH4, absolutely incorrect. Those who are saying NaBH4 cannot reduce the double bond of alkene. I said alkene double bond भी खत्म हो गया था. ये होता है organic synthesis. बड़ी simple सी चीजें हैं. So I used, instead of NaBH4, I used hydrogen and nickel solid and heated it. Yeah. Next question. If I have ester, ketone, aldehyde, and alkene in a particular organic molecule, which just means I have the ester functional group, I have the ketone functional group, I have the aldehyde functional group, I have the alkene functional group, right? नो, हाइड्रोजन और निकल नहीं होता शहीर, क्या हो गया, हाइड्रोजन एंड निकल सॉलिड इज द कैटलिस्ट एंड यू हीट। एल्कीन से एल्कीन में ऐसे ही जाते हैं, ओ लेवल्स में पड़ा हुआ है, और नहीं है, एंड है। अच्छा, so I have ester, ketone, aldehyde, and alkene, and then I reduced it, and I still had ester, I had ester, I had secondary alcohol, primary alcohol, and I had alkene. So ester and alkene were still there. Which reducing agent did I use? Now you've all got it. NaBH4. See? Easy. आसान है। तो सारी ऑर्गेनिक सिंथेसिस अब जनाबे वाला ये। लेट्स स्टार्ट डूइंग ऑर्गेनिक सिंथेसिस क्वेश्चंस। नमाज का टाइम तो होने लगा है, क्या हिसाब किताब है? नमाज फिक्स टाइम पे पढ़ें ज़रा। नमाज टाइमिंग 4:30 पे होती है यार, क्या हो 5 बजे होती है, क्या होगी? किसने लिखा है नमाज टाइमिंग हो गई है? अच्छा, इट्स ओके यार, वी आर ऑल मुस्लिम्स, प्लीज़ do not segregate, do not spread segregation, बस we are all Muslims. ज़रा ऐसी बातें ना करो, ठीक है? Yesterday you were talking about, you know, X and all of that stuff. It's okay. It's okay when it comes, but religious sentiments, please don't make fun of religious sentiments. ठीक है ना? चलो परफेक्ट, ख़त्म। अब मैं डालता हूँ, मेरी मेमोरी इखलास हो गई है यार, मेरी दिमाग की मेमोरी भी ना वड़ बुड़ गई है कहीं, दिमाग की मेमोरी भी मेरी ख़त्म है, बस मुकम्मल तौर पे ख़त्म है, मुकम्मल तौर पे वड़ बुड़ गई है। माई ब्रेन इज़ हर्टिंग। अच्छा, वी आर गोना स्टार्ट एट 4:15। 4:15, चलो 5 मिनट ब्रेक ले लेते हैं, 5 मिनट ब्रेक ले लेते हैं, 5 मिनट्स ब्रेक, 5 मिनट ब्रेक ले लेते हैं। आई एम गोना पॉज द रिकॉर्डिंग, आई रिज्यूम द रिकॉर्डिंग। आज तख्त ने तख्त नु की करना, अच्छा तख्त तख्त तक ओते थे, समथिंग लाइक दैट। सर ए लेवल में साइंस लेके यूनी में अकाउंटिंग, आई डिड नॉट गो टू यूनी, आई जस्ट, अच्छा, I am 21, somebody saying I'm 22, somebody saying I'm 23, he's at best 23, somebody saying he's at best 28. Sir, grades matter, subjects don't. Sir, do you like abide performs? I don't know what that means. आज तख्त ने तख्त की करना, yeah. चले जी, the moment of truth, the moment you all have been waiting for. Organic synthesis. Organic synthesis is not something new. The moment you all have been waiting for, organic synthesis, it's not something new, it's now just practice. I've given you guys mind maps, and it's about a 5-hour class that you guys can watch on the portal, or it's split into 2 parts if you're watching onto YouTube. After you're done with those 2 parts, which says complete organic chemistry summary, marathon, whatever, blah, 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 you guys now need to just practice with me, and it's a piece of cake. What exactly is organic synthesis? It's just a fancy word of saying making different molecules and knowing what's the intermediate between them and what is the reagent and what is this and right. So let's do all of that stuff now. I am gonna make you guys do some difficult examples. The examiner will never ever make it this difficult, but I am gonna make it difficult for you guys to be able to think better, right? Because examiner will give you a lot of hints in between. I won't, because I want you guys to then find the exam questions very easy. So I'm gonna start off with an organic molecule. Let's start off with this organic molecule. Tuck and a tuck and a tuck tuck tuck. This happened, and then what happened? This happened, and then something like this happened. OH. Sir, your hair in a fluff. मरे चुप कर जाओ, मेरा दिमाग काम करना छोड़ देगा. COOH, let's suppose. Sir, बताएं, what is X? Shabash, tell me what X is, and what are the reagents? What are the conditions? हाँ जी बताएं, what is X? What is the reagent and the condition here? What is the reagent and condition here? Now let me teach you how you guys can easily walk your thought process or use your thought process in organic synthesis. You have two major thought processes in organic synthesis, and the thought process is the thought process that I use and that I would want all of you guys to use is: what is your starting stage and what is your ending stage? Can you walk backwards and can you walk forwards? This is all you need to know. Do you walk backwards or do you walk forward? And what are the potential reactions that a particular functional group can have? So 3 questions you keep in your brain. What functional group do you have? What are the potential reactions that that functional group can do? Can you walk forwards? Can you walk backwards? You have to look at it from a zoomed out perspective. Never ever start naming this guy. Never start naming this guy. For crying out loud, you are going to cook yourself. I am going to say simple concepts. Okay, look at my simple concept. I use the broader terminology for it. I say, hey, this is a ketone. This is the broader terminology for it. And I say, wait, what has actually happened here? This is an OH and this is a COOH. So this fella is something hydroxy. This is hydroxy and this is acid. So it's like a hydroxy acid that I have. What that means is that X must be something in between. And if you use your brain, you've studied something known as hydroxynitrile, haven't you? And then you know that the hydroxynitrile can further be acidified. Hydroxynitrile can further be acidified and give you carboxylic acid. And to further enhance my to further have a credibility in my thought process, to further tell myself, yeah, I am thinking correct. Also, you know that the cyanide ion will increase the number of the nitrile, means whenever a nitrile forms a C bonds, you are going to have one more carbon compared to your starting stage. And if you check this out, see, you have 3 nodes here, 1, 2, 3. But when you check out the right stage, you have 1, 2, 3 nodes here and 1 more here. So you realize that, hey, you went from 3 carbons to 4, which means that there must be a CN involved in between. So see, by looking at it from a very hawk eye perspective like this, I realize that this must be a cyanide forming. And so ketones, how do they end up with nitriles? How do you end up from ketones into hydroxynitriles? So the reaction is NaCN and KCN aqueous. HCN, NaCN or KCN, and then followed and as well as HCN aqueous, heat under reflux. And so what you realize, hey, instead of this ketone, I end up with hydroxynitrile. So this double bonded to O is going to become OH. This double bonded to O will become OH, and your 3 carbons are like so, 1, 2, 3. I'll show the 3 carbons like this, 1, 2, 3. I've shown these 3 carbons like so, and this fella will become the CN, a hydroxynitrile. Done. And what is this reaction called? This reaction is called nucleophilic substitution reaction. How easy is this? And so then how does hydroxynitrile go into carboxylic acid? How? The CN changed into CC. You check out the differences between this fella and this fella. What is the difference? This is CN, this is COOH, which means you use dilute acid, dilute HCl effectively, and heat. And what is this reaction called? This is called hydrolysis. That's all. These are called 2-step conversions. Asan? Sir, can you write steps to solve such maps type of questions? This is what do you mean steps? This is how they'll be asked. The examiner will give you an empty space here, and the examiner will give you what are the reagents here and here. Normally the examiner does not test such difficult questions. The examiner will probably give you X. He'll not give you 1 and 2, but he'll probably give you X. एक और करूं चाहे बताते जाएं बस. अब ऑर्गेनिक केमिस्ट्री खत्म है भाई, अब आप खुद करें. खत्म है. This guy goes into this. बताएं. What is reaction number 3? This guy goes into this. What's 3? What has happened? Check out the differences, sir. Check out the differences. You went from a ketone to a secondary alcohol. See, this is how you think about it. Ketones is secondary alcohol. Okay, how do I go from ketone to secondary alcohol? Oh, that's reduction. See, I'm not even concerned about the name. I'm just checking changes in functional groups. So it's called reduction. I represent it with an H. What is the reducing agent that you can use? You can write any reducing agent here. You can use LiAlH4 in dry ether. Because if it's aqueous, it's going to be very, very explosive. That's why NaBH4 is in aqueous state, because it's a slightly milder oxidizing agent. Reducing agent. What the hell was I saying? And hydrogen and nickel solid. And this is heat. In all these 3 cases, you also heat. So you could use either or with heat. सर देयर आर ऑलवेज मोलेकुलर फार्मूलाज गिवन. नो नो, ऑर्गेनिक सिंथेसिस में आपको कभी मोलेकुलर फार्मूला ऐसा नहीं देंगे, आपको स्ट्रक्चर्स बना के देंगे और आपने भी बनाने होंगे. बट मोलेकुलर फार्मूला फिर तो आपकी मोलेकुलर फार्मूला और ये चीज़ें में मसले हैं ना, वो पहले स्ट्रेंथन करें. स्ट्रक्चरल फार्मूलाज, मोलेकुलर फार्मूलाज, स्ट्रक्चरल फार्मूलाज. आई थिंक यू आर टॉकिंग अबाउट स्ट्रक्चरल फार्मूलाज. You need to be strengthened. You need to have strengthened structural formulas, molecular formulas, skeletal formulas. Other than this, you can't walk your way across organic chemistry, can you? What if I say this? Yellow precipitate or orange precipitate. What is 4? Reaction name, condensation reaction. What did you use? 2,4-DNPH. Sir, victory sign need a picture. Woo! Zoom out. बस यही है सर सलमान. You literally, literally bossing me around, guys. Very bad. Very bad. कोई और करो. Let me do one more. आज तख्त ने की करना. आज तख्त NaCN in ethanol and heat under reflux. हाँ जी बताएं. What forms? And then whatever forms, उसके साथ मैं क्या करूं? अच्छा तख्त ने की करना. Reducing. So this is part 1. This is part 2. हाँ जी. Halo addition. What the hell is halo addition? This is halogen atoms here, haloalkenes, halogen atoms here, right here. Then you use NaCN in ethanol. NaCN in ethanol means cyanide ion. It's what? Haloalkenes reacting with cyanide ions. It's nucleophilic substitution reaction number 1. And when it reacts with cyanide ions, what happens? Sir, your nitriles forms, not hydroxynitrile. It's a nucleophilic substitution here. Hydroxynitrile nahi banenge, nitriles banenge. Hydroxynitrile forms when in carbonyl compounds, when they go into, when they undergo nucleophilic addition reaction. So what is 1? 1 will just have CN and CN. Instead of the BRs, you're just going to have CN and CN. See, this is how you need to think about it. No mechanism, no whatsoever. And if you want to show the proper structure for it, this is how you show the proper. You either show it like this, CN, CN, but I don't recommend showing it like this because this is incorrect skeletal for it. This is the proper skeletal for it. See, this fella, this node right here, this represents a carbon. This node right here, this represents a carbon. This is what formed. And then I said you reduced this. You reduced this fella. But reduced छोड़ दें. What the hell am I doing? Reduced छोड़ दें. What am I gonna do? What am I gonna do next? I'm gonna form something. I'm gonna form something. Hello honey bunny, feeling something. Hello honey bunny. Angie, what have I done? Angie, what is part 2? Feeling something. Hello honey. Yes, it's acidified. What have I used? I've used dilute acid. Which acid? Normally HCl. What is the reaction name? It's called hydrolysis. Don't say acidify, call it hydrolysis. Hello honey bunny. हुए फासले, हुए सिलसिले. What happens here? Which reducing agent can you use? What will happen to carboxylic acid if you reduce them? Which reducing agent? Obviously LiAlH4 in dry ether. And what will happen? See, this carboxylic acid is no longer a carboxylic acid. It's going to become an alcohol. This carboxylic acid, no longer a carboxylic acid, becomes an alcohol. See, carbon, OH. So it's carboxylic acid, now they are alcohols. You the real Kavish. No. Shut up. Okay, next. Feeling something, something. Hello, honey bunny. Yeah. करें या रिलैक्स. अच्छा. दूँ आपको मुश्किल मुश्किल सी चीज़ दूँ. मुश्किल सी चीज़ दूँ कि नहीं. Sir, one more pick for me. 3 hours completed. हुए फासले, हुए सिलसिले, जाना ना 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 ना, जाना ना. मैंने जो खुशी मैंने ना सकी. मेरी ये दुआ है कि तेरा जीवन जो ही पढ़ता रहे सारी ख्वाहिशें हाँ पूरी. सर ये क्या क्वेश्चन है. क्वेश्चन है, करते जाओ भाई, करते जाओ. बताता हूँ क्या क्वेश्चन है. Feeling something, something. Hello, honey bunny. Feeling something, something. अच्छा. चाहे तेरे संग जाए तू जहाँ, मेरी ये दुआ है कि तेरा जीवन यूं ही जड़ता रहे सारी ख्वाहिशें हों पूरी. सर ब्रेकअप हर्ट्स और ऑर्गेनिक पास्ट पेपर्स तो आपको ज़्यादा पता होगा. Yeah. I will pause the recording here and then I'll start. मैं दिमाग से बना रहा हूँ ना यार, टाइम लग रहा है, तो मैं क्या करूँ, किस दीवार पर सर मारूँ। अच्छा चलिए, रोज़ा लग रहा है। अच्छा Okay, I've resumed the recording. Effectively, this will cover a lot of things for you all. Almost all the type of questions that can be asked in organic synthesis, I've covered them. We are starting off with this bit right here. I'll call this 1. I'll call this 2. I'll call this 3. I'll call this like 4. I'll call this, okay, no, not this 4. I'll call this 4. If you guys want, you can try it on your own. This is 5. This is 6, this is 7, this is 8, and this is 9, and this would be 10, this is 11, okay, that's 12, that's 13, this fella is 14, and then this is 15. Try it out on your own if you want, you know. If you want to try it, give it a try, give it a try. Acha, I'll also add one more thing here. Acha, 3.5. Yeah. So this is 3.5. Chalo ji. Sir, is this helpful for O-level students too? Faria, what are you doing here? This is not an O-level class. Do you think this is helpful for O-level? Have you seen this in O-level? Have you seen these things in O-level? Faria, क्या कर रही हैं? You're gonna confuse yourself big time. Please don't do any of this thing, यार. क्या हो गया? चलो जी. अच्छा, you are not in O levels. अच्छा, फिर सही है. O level में क्या आपने ये पढ़ा था फारिया? There is also a student of mine in O levels. चलो जी, let's try this. If you want, you guys can do it on your own. If not, then I'll do it. I'll give you guys 5-6 minutes. I'll zoom out a little. Give you guys 5-6 minutes to do this. This is effectively all the types of questions the examiner can ask. सही है भाई, काफ़ी है यार. चलता रहे सारी ख्वाहिशें हो पूरी. Sir, only 13 students left. No, only 12. What am I? We started off with so many soldiers. Soldiers started to die in between. Oh, one more soldier is here. Our soldiers started to die one by one. शहीद होते रहे. थक गया हूँ यार. I don't want to do it. I don't want to solve this. I'm tired. I'm gonna kill myself. What am I doing in life? What am I doing in life? So check Insta. Oh, this is so cute. Thank you so much, Ali Afnan. I love this. Love this. Thank you, Jeete. Beautiful. कार्बोक्सिल केम को भी टैग टू कर दें. सारी ख्वाहिशें हो पूरी. शाबा करें, डू इट ऑन योर ओन. मिस करवाएं फॉर रियल. करें, डू इट ऑन योर ओन. शाबाश. आई एम गोना पॉज द रिकॉर्डिंग फॉर अ बिट. डू इट. करें. Resumed the recording. Let's start doing them one by one. So I'm actually very tired, but okay. See, you have to solve these questions like this. See, this is a haloalkane. This is an alkene. How do you go from haloalkane to alkene? See, I'm not naming anything. I'm not noticing anything. Just haloalkane. Broadly, you need to know what you're talking about. So haloalkane to alkene. How do you go from haloalkane to alkene? NaOH. It's an elimination reaction. First, let's also name it. So let's call it the reaction. I'll write the reaction name with blue. So elimination reaction, done. And in green I'll write the condition. So NaOH, and this is ethanolic because we want the OH to act as a base, and then heat under reflux, done. Then number two says alkenes go into diols. How do you see? This is how I think about it. Alkene to diol. How do alkenes go into diol? Cold dilute acidified potassium magnate. What's the name? The name, it's called oxidation reaction. The name. Done. Next. Part 3. Alkenes into carboxylic acid. Now this is beautiful. See, what I've done here is I've just shown you one product. What you realize is the double bond has ruptured, and in both cases you ended up with a carboxylic acid which looked exactly the same. In both cases you end up with ethanoic acid, right? You see there is a hydrogen here and there is an alkyl group here. So the hydrogen will get again the O, there will be COH, and this double bond rupture will become O here. So it will be COOH, and this is 1, 2, 2, 2 carbons, right? So what I've effectively done is I've just shown you one of the product is it's a symmetrical alkene, and it's going to give you guys 2 moles of this carboxylic acid, right? So that's the idea. So what is part 3? What is part 3, everybody? You end up with carboxylic acid, and I've used hot acidified, sorry, why am I using blue color? Hot acidified aqueous potassium, hot concentrated acidified aqueous potassium manganate, and this is again oxidation. Actually, I want to add one more thing here. 2 में 2.1, I want to add 2.1 here, which is this. What is this? What has happened is you've taken this alcohol and it became a salt. How? Because you added a sodium metal here. It will react with sodium metal. And this is as effectively sodium reacting with the OH. It's effectively a displacement reaction. अच्छा, ऑक्सीडेशन के लिए पोटेशियम मैंगनेट नहीं इस्तेमाल. नो, दिस इज रप्चरिंग द बॉन्ड, द कार्बन कार्बन डबल बॉन्ड. एल्कीन्स, इफ यू वांट to rupture the carbon carbon double bond, you have to use hot concentrated potassium manganate. If you want to add diols, cold dilute acidified potassium manganate. Come on, yaar, I've done the entire mind map. Go watch the recording. Then next, part 3, you have the carboxylic acid and the carboxylic acid went into something like this. Now this is beautiful. It's an ester. See, C double bonded to O, and this part came from the alcohol. How many carbons came from the alcohol? 1, 2, 3. 3 carbons came from the alcohol. So you have a reagent that you're using, which is effectively metheth propan 1-ol. This is 3, and this fella is gonna be OH. Only then is this fella gonna form metheth. It's propyl metheth ethanoate. So propyl ethanoate is this fella. So you must have used propan 1-ol, 1, 2, 3, propan 1-ol, and or propanol, and this guy is metheth ethanoic acid. So this will become ethanoate, this will become propyl, right? So this we are using, and we are using conch acid and heat. This is how esterification happens. Conch phosphoric acid you could use. Sir, for 2 shouldn't we use H2PO4? I have not taught anything of such sort. डायोल्स के लिए आपको ये पता नहीं किसने पढ़ाया, मैंने नहीं पढ़ाया ये. Who said H2PO4 for diols? What's wrong? Alkenes, diols, I don't know what you're saying. Acha, done? This is also done, that's also done, that's also done. And esterification is effectively also a condensation reaction, by the way. Yeah. Then 4 is done, 3.5 is done. Then where do we go? We go here. So haloalkane went into a nitrile. See, this is how I think about it. Haloalkane going into a nitrile. Haloalkane into a nitrile. How? Well, you must have used sodium cyanide then in ethanol, obviously, because if it's aqueous, then the OH can actually potentially cause it to make the alcohol. And then heat under reflux, you end up with nitriles. And then this nitrile went into carboxylic acid, which means I've used dilute acid. And what was this reaction called? This reaction again is a nucleophilic substitution reaction. And then this is hydrolysis, by the way. It's hydrolysis. You use dilute acid, aka dilute hydrochloric acid, or dilute sulfuric acid, doesn't really make a difference. Then carboxylic acid goes into an alcohol. How? Obviously, then that's reduction. And which reducing agent do you use? Only LiAlH4 in dry ether can reduce carboxylic acid to alcohol, primary alcohol. Then it's obviously reduction. I've added H here, but you can write reduction reaction. Then this primary alcohol is reacted with potassium magnate, acidified aqueous potassium magnate, and heat under reflux. And you know, if you have a primary, how do you know if it's a primary alcohol? See, this is the carbon which has the OH, and it's only bonded to one carbon, one alkyl group, this entire thing. So primary alcohol, if you were to heat under reflux, it'll make carboxylic acid again. So it's going to form thut, C double bonded to OH, the same thing, the same fella is going to form again. Right? So it will form the same carboxylic acid. Then what is part 8? You use a slightly milder oxidizing agent, and then you heat and distill it. You know, primary alcohol, if you heat and distill using potassium dichromate acidified aqueous, it will form aldehyde. Tuck. That's the carbon which had the OH. This will become double bonded to O, and this is the H, right? If it's your choice to show the H if you want, or you can even not show the H. It's absolutely okay. It's fine. So that's the aldehyde. Then part 8 is also done, and this is again, what is it called? This is called, both these reactions are called what? They're called oxidation reaction. This is also oxidation, and that's also oxidation. Done. Then we move on to part 9. Part 9 mein haloalkane goes into alcohol plus a cream precipitate. What that means is, see, it's a nucleophilic substitution reaction. We all know that, haloalkanes to alcohols. But there's also a cream precipitate forming, which is obviously possible if AgBr were to form. That means that you've not used the usual sodium hydroxide aqueous and heat under reflux. No. You've not used this the usual. No. You've actually also included silver in it. And you know that there's also one more reagent that we could use, which is silver nitrate aqueous and heat under reflux. So effectively, you've not used sodium hydroxide aqueous heat under reflux, although this is the usual. We've used silver nitrate aqueous. The OH minus acts as a nucleophile. All of this happens, heat under reflux. And the silver ion, it forms a bond with the bromide and forms AgBr. Done. So that's 9. Part 10 is what? You have the alcohol going into alkene. How do alcohols go into alkene? Alcohols go into alkene. This is called elimination reaction or dehydration reaction / dehydration, in which water is removed, right? And how does it happen? You either use Al2O3 and heat, or you use concentrated sulfuric acid. Remember to use conc sulfuric acid because that's a dehydrating agent, and heat. Done. See, this is organic synthesis for you. There's nothing new to it. Alcohols, aren't alcohols and diols the same thing? Yes, diol is just two alcohols, two OHs. Yeah, the same thing. So then the alcohol goes into haloalkane. How do alcohols go into haloalkane? And it's a Cl atom. It's up to you. You could use HCl and heat. You could use PCl5 at RTP. You could use SOCl2 at RTP. Normally we say no heat is needed with SOCl2, but sometimes the examiner writes heat, so we'll write heat. But in SOCl2 it can happen at RTP, by the way. And it can happen with PCl3 and heat. It can happen with NaCl plus H2SO4, which will form, and heat obviously, because this will form HCl, and then that HCl, dry HCl, would react, and this is conc H2SO4, by the way, would react, would be heated, and this fella would form. So you could use either or. You could use this, any of these. Next. Done. Then part 12 says you go from alcohol into nitrile. How do you go from alcohols into nitriles? How do you go from alcohol? Sir, you taught something. Sir, when you taught alkenes, you taught to go from alkenes to alcohols using phosphoric acid. Yeah, this thing, alkene to alcohol, that was electrophilic addition reaction. I think you've missed out on part 1, Maz. You've not watched part 1 carefully. Alkenes can go into diols with cold dilute acidified potassium magnate. Alkenes to alcohol, just one OH, that would be electrophilic addition. And here the double bond break, you have two OHs. Please do not confuse it with the hydration reaction, the electrophilic addition reaction. Please do not confuse it with that. Okay, how do you go from alcohols to nitriles? Alcohol to nitrile, no direct method is there. So I'll just make an in-between thing, right? So 12 ki jagah, what would I do? Instead of 12, I would make 12.1. आंखें मेरी तक गई हैं यार, आंखें मेरी तक गई हैं. 12 ये मैंने गलत बनाया. I made this question on my own, ना? So you guys have to bear with me however I make it. Yes, please. bear with me. Can you guys bear with me? इसके बीच का कुछ बना देते हैं. Sir, can we also use HCl? I literally wrote HCl usage. You can absolutely do that. Bilkul, you can do that. Bilkul, you can do that. So we can't go into nitriles here. So I'm just gonna make this like into iodo, and then we're gonna go here. So instead of 12, just gonna call this 12. This is 12. I made this question now. And then this would be called 12.1. So what is 12? Going into iodo, you can use HI and heat, or what you could do is you could use red phosphorus and I2, but since they are both solids, there needs to be moisture involved. So damp red phosphorus and I2 and heat. Done. That's how you end up with the iodo fella. And then this is actually a substitution reaction. This is substitution reaction. This is also a substitution reaction. Then 12.1, haloalkane into nitrile, again NaCN or KCN in ethanol and heat under reflux. And obviously this again is nucleophilic substitution reaction. Then it's and I'll also make 12.2 here. What is this, by the way? Tuck, tuck, tuck. What is this? This is what? Excess ammonia. Again, nucleophilic substitution reaction. And see, an amine has formed. So haloalkane to amines. Excess ammonia, heat in a sealed tube under high pressure. Done. That's what forms. Then nitriles to amines. So nitriles to amines. Now, obviously, you haven't studied nitriles to amines, have you? You'll study this in A2 chemistry. But the examiner, see, as an examiner, I've written LiAlH4. So what is the name of this reaction? This reaction is basically a reduction reaction, because LiAlH4 is a reducing agent. That's the only reason why I gave you guys this bit. Done. And this again is nucleophilic substitution, this one. So this is reduction. How did you know? Is this part of your course? No, 13 is not part of my course. But the reason why I gave it to you guys is to understand that the examiner can test you with some things like this. And you, if he's saying LiAlH4 is used, that means that's a reducing agent, and therefore this reaction is called reduction. That's the only reason why I added it. Next, everything else is done. The last bit, 14. The alcohol is treated with alkaline I2 and warm. Now, alkaline I2 means NaOH plus I2. And if NaOH plus I2 is used, you realize that, hey, this is the CH3 fella. See, this is the CH3 guy. So if you have a secondary alcohol, it'll give you a product with alkaline I2 and warm. Because the secondary alcohol will convert itself into what? It'll convert itself into a ketone, and once that ketone forms, this CH3 is gonna break. See, it'll first convert like this. After you use alkaline I2 and warm, first thing that'll happen to this secondary alcohol is that it will convert into a ketone, and then simultaneously this fella starts to break the CH3CO, because see, this CH3CO is actually confirmed with alkaline I2 and warm, right? So this fella breaks, and once this fella breaks, you're gonna have what? Once this fella breaks, you're going to end up with triiodomethane, CHI3. This is what you end up with, which is a yellow PPT. And this part becomes the salt, which is O minus and Na plus. And then the same salt can be further acidified, and this reaction is called iodoform. Iodoform, or triiodomethane reaction. So this is iodoform, and then if you add dilute acid to it and heat, obviously what's going to happen? This is hydrolysis, and you're going to end up with acid. 1, 2, 3, that's the acid. This is all. This is every single type of mechanism that the examiner can test, and other than this, I don't think there's anything that I've not covered here. Every single type I've covered in this. That's it, guys. I hope you guys enjoyed. I'm gonna pray right now, and then I'll come back and solve some 2024 set MCQs. But I think I'll do that tonight. How about we do that tonight at 10 p.m. probably, because my head is now bursting. I can't do this anymore. I'm tired. I hope you guys enjoyed. This will be uploaded onto YouTube. 10 p.m. inshallah, I'll do past paper questions of organic synthesis with you all, and you guys will see how easy it is. Sir, thank you for your efforts. Love you too, Maz. Love you all. Aunt alcohol. I think I answered that tonight. Okay, tonight. It was pretty productive. Yes, Murtaza. मेरी तो बस हो गई है. बज बुझ गई है मेरी तो बच गई है बच. I'll upload these things on your portal. And I upload this part 2 on the on YouTube. Thank you. Welcome guys. My pleasure. Love you all. Bye. Ciao. Allah Hafiz. Bye.